There is a kind of star that does not explode, does not collapse into a black hole, and does not even look particularly unusual through a telescope. From a distance, it would seem almost peaceful, a small dim point of light, barely 12 miles across, spinning quietly in the dark. And yet, if one of these objects passed within a few hundred miles of Earth, it would not need to touch us at all. It would not need to release a single particle in our direction. Simply existing nearby would be enough to scramble the data on every hard drive on the planet, rewrite the chemistry in our blood, and quite possibly end every form of complex life within minutes. Astronomers have a name for this object. They call it a magnetar. Tonight, we are going to explore why many physicists consider magnetars more dangerous, pound for pound, than supernovae, more violent in their local effects than black holes, and in some ways stranger than almost anything else known to exist in the universe. We will look at how something so small could store more energy in its magnetic field than the Sun produces in 100,000 years. We will examine the night in 2004, when a magnetar 50,000 light-years away briefly outshone every other source of gamma rays in the sky combined, and how astronomers realized, with some unease, that they had been looking directly at one of the most energetic events ever recorded by human instruments. By the end of this journey, you will understand why a star can become a weapon without firing anything, why magnetars are quietly reshaping our understanding of physics at its most extreme limits, and why scientists still cannot fully explain how something this powerful is even possible. To understand any of that, though, we have to start somewhere far less exotic. We have to start with an ordinary star, much like our own, and ask what happens to it when it finally runs out of fuel. Every star is, in a sense, fighting a war against itself. Gravity is constantly trying to crush the star inward, compressing it toward a single point. The only thing holding that collapse at bay is the outward pressure generated by nuclear fusion in the core, the same process that makes our sun shine. For billions of years, in the case of a star like the Sun, this is a stable standoff. Gravity pulls in, fusion pushes out. The star exists in a kind of suspended argument with itself, but fuel runs out eventually. And what happens next depends almost entirely on how much mass the star had to begin with. A star like our Sun, when its fuel is exhausted, will swell into a red giant, shed its outer layers, and settle down as a white dwarf, a dense, slowly cooling ember about the size of Earth. It is a quiet ending, unremarkable even on a cosmic scale. Our own Sun is expected to follow this path in roughly 5 billion years, long after Earth itself has likely become uninhabitable from the Sun's gradually increasing brightness alone. But for a star considerably more massive than the Sun, the ending is anything but quiet. When a star with somewhere between about 8 and 25 times the mass of our Sun reaches the end of its life, its core can no longer generate enough outward pressure to resist gravity. The core collapses in less than a second. Material falls inward at a significant fraction of the speed of light, slams into the dense center, and rebounds outward in a shockwave that tears the rest of the star apart. This is a supernova, one of the most violent events in the observable universe, briefly outshining an entire galaxy of ordinary stars. What is left behind after that explosion scatters most of the star's material into space is the leftover core. And under the right conditions, that leftover core becomes a neutron star. This is where the story starts to become strange. A neutron star is what happens when gravity wins almost completely against the forces holding ordinary matter together. The collapse is so violent that electrons are forced to merge with protons, transforming them into neutrons. The result is an object made almost entirely of neutrons, packed together at a density that the human mind struggles to process. A teaspoon of neutron star material would weigh roughly as much as a mountain. Some estimates place it at around 1 billion tons. A neutron star typically has a diameter of only about 12 to 15 miles, roughly the size of a city, yet it contains more mass than our entire sun. Consider what that means in practical terms. If you could somehow take all the mass of our sun, an object so large that more than 1 million Earths could fit inside it, and compress that mass down into something the size of a metropolitan area, you would have approximated the density of a neutron star. This is not a metaphor stretched for dramatic effect. It is, within an order of magnitude, the literal physical situation. If you tried to stand on the surface of a neutron star and somehow survived the experience, you would weigh, in an instant, more than 100 billion times what you weigh on Earth. The gravity is so extreme that light itself bends visibly around the star's curve. Photons emitted from the far side of the surface can be redirected toward an observer, meaning that in theory, you could see more than half the star's surface at once, an effect produced purely by the way the star's mass warps the space around it. Coin dropped from a height of just 1 meter above a neutron star's surface would strike that surface at a significant fraction of the speed of light, releasing an amount of energy comparable to a small explosive device, purely from the act of falling such a short distance. Most neutron stars, once formed, settle into a kind of stable, predictable existence. They spin rapidly, often dozens or even hundreds of times per second. Many of them emit beams of radiation from their magnetic poles. And if those beams happen to sweep across Earth as the star rotates, we detect them as a pulsar, a star that appears to blink with mechanical regularity, like a cosmic lighthouse. Pulsars were first detected in 1967 by a graduate student named Jocelyn Bell Burnell, working at the Mullard Radio Astronomy Observatory in England. The signal she found was so precisely regular, repeating every little over a second with what seemed like impossible mechanical perfection, that for a brief, almost comic moment, some astronomers in her research group jokingly labeled it LGM-1 for Little Green Men, wondering whether they had picked up a signal from an alien civilization. The regularity was simply too perfect to look natural at first glance. It was natural. It was just a different kind of perfection. A dead star's leftover core, spinning with mechanical precision, because there was nothing left inside it to disrupt the rhythm. The discovery would eventually contribute to a Nobel Prize in Physics, awarded in 1974, though notably to Bell Burnell's supervisor, rather than to Bell Burnell herself, a decision that remains a point of discussion within the history of astronomy to this day. Most neutron stars, then, are dangerous in the way you would expect a hyperdense, rapidly rotating stellar corpse to be dangerous. They are deadly to approach, fascinating to observe from a distance, and largely predictable once you understand the physics governing them. Thousands of ordinary pulsars have now been catalogued across the galaxy, their rotational periods measured with extraordinary precision, some spinning so fast and so steadily that their timing rivals the best atomic clocks built by human engineers. Magnetars are not like most neutron stars. Somewhere in the chaos of a collapsing stellar core, a small fraction of neutron stars are born with something extra, a magnetic field of a magnitude that strains the limits of what physics says should be achievable. An ordinary neutron star already has a magnetic field that is almost incomprehensibly strong compared to anything found on Earth. A typical neutron star's field might be around 1 trillion times stronger than Earth's magnetic field. That number alone is difficult to hold in the mind. Earth's magnetic field, the one that deflects a compass needle and protects us from much of the sun's charged particle radiation, measures roughly half a Gauss at the surface. A typical neutron star's field measures in the trillions of Gauss. A magnetar's magnetic field is not merely strong, it is strong, even by the standards of the most extreme objects already known to exist. Magnetars typically have magnetic fields ranging from roughly 1,000 to 10,000 times stronger than an ordinary neutron star, which itself was already trillions of times stronger than anything found on Earth. The numbers compound on top of each other until they stop feeling like numbers and start feeling more like a kind of physical absurdity. Expressed directly, a magnetar's surface field can reach somewhere in the range of 10 to the 15th power Gauss, a figure so far removed from ordinary experience that physicists sometimes prefer to express it through its effects rather than the raw number itself. And this is where the first genuine mystery of the documentary appears, because nobody fully agrees on how a magnetic field of that magnitude is even produced. The leading explanation involves something called a dynamo effect, similar in principle to the process that generates Earth's own magnetic field, but operating under conditions almost beyond imagining. Earth's magnetic field arises from the slow churning of molten iron in our planet's outer core, a relatively gentle process unfolding over millions of years. The dynamo proposed for magnetars is the same basic physical principle, but compressed into an almost unimaginably violent and brief window of time. In the first few seconds after a massive star's core collapses, the newly formed neutron star is spinning extraordinarily fast, sometimes completing a full rotation in under a few milliseconds, while extremely hot material churns and convects within it. If the conditions are exactly right, this rapid rotation, combined with violent internal convection, can act like a natural amplifier, winding up and intensifying the star's magnetic field to staggering levels within the first 10 to 20 seconds of the star's existence as a neutron star. Theoretical models suggest that for this amplification to work efficiently, the newborn neutron star's rotation period needs to be remarkably short, on the order of a few milliseconds, close to the fastest rotation rates that the laws of physics would even permit a neutron star to sustain without flying apart from centrifugal stress. The key phrase there is, if the conditions are exactly right. Most neutron stars do not end up as magnetars. The window of circumstances that produces this dynamo amplification appears to be narrow, and astronomers are still working out exactly what determines whether a given collapsing core falls inside that window or outside of it. Some research has suggested that the original star's rotation rate, before it ever collapsed, along with the presence of any pre-existing magnetic field inherited from the star's earlier life, may play a decisive role in determining the outcome. A star that happened to be an unusually fast rotator in life might be more likely to produce a magnetar in death. This is the first thread we will return to throughout this documentary. Magnetars are not simply neutron stars with strong magnetic fields. They appear to be the product of a very particular, very brief, and still only partially established moment of stellar birth, locked in place forever afterward. It would be reasonable at this point to wonder whether most dangerous star in existence is simply dramatic language. Black holes, after all, have a reputation for danger that magnetars do not commonly share in popular culture. Supernovae are associated with planetary annihilation. Magnetars, by comparison, sound almost obscure. But danger in physics is not always about scale of destruction in an absolute sense. It is often about a combination of factors. How much energy is involved, how that energy is delivered, how far its effects can reach, and how little warning exists before something happens. A black hole, for all its terrifying reputation, is in most respects a predictable object. Stay far enough away from its event horizon, and a black hole behaves, gravitationally, exactly like any other object of equivalent mass. There is no invisible field reaching out across light years to interfere with your equipment. If our sun were somehow replaced with a black hole of identical mass, a thought experiment astronomers occasionally use to illustrate gravitational behavior, Earth's orbit would not change at all. We would simply lose our light and heat. The danger of a black hole is overwhelmingly local. It matters enormously if you are close, and barely at all if you are far. A magnetar is different, because its primary danger is not gravity. It is the magnetic field itself, extending outward in a way that can interfere with matter, electronics, and potentially biology at ranges that would be entirely safe around an ordinary star, or even an ordinary black hole of similar mass. This is the heart of the mystery we are unpacking tonight. How can an object the size of a city possess a field capable of disrupting matter at planetary distances? And what does that reveal about the limits of physics? To answer that, we need to look more closely at what a magnetic field of this magnitude actually does to matter. When most of us think of a magnetic field, we think of refrigerator magnets or compass needles. Useful, but unthreatening. The idea that a magnetic field could be dangerous in any serious sense feels almost contradictory to our everyday experience. We grow up handling magnets, sticking them to surfaces, watching them attract or repel one another with a gentle, almost playful resistance. Nothing about that experience prepares us to think of a magnetic field as something that could end a life. This intuition breaks down completely once you reach the field strengths involved with a magnetar. At the surface of a magnetar, the magnetic field is strong enough to begin physically distorting atoms. Under normal conditions, an atom's electron cloud is roughly spherical, a fuzzy probability distribution surrounding the nucleus. In a field as intense as a magnetar's, that cloud is forced to elongate and compress into a thin, cigar-like shape, stretched along the direction of the magnetic field lines. This is not a minor distortion. Calculations suggest that, in fields of this magnitude, hydrogen atoms can become roughly 200 times narrower than they are normally, compressed into elongated shapes that barely resemble the atoms found in ordinary chemistry. Physicists sometimes describe this state using the term magnetized atoms, a category of matter that essentially does not exist anywhere else in the observable universe outside the immediate vicinity of a neutron star or magnetar. The chemical bonds and reactions that make up biology, and indeed all of ordinary chemistry, depend on the specific shapes and behaviors of electron clouds around atoms. distort those shapes enough, and the basic chemistry that makes life, and indeed most matter as we understand it, possible, would simply cease to function in any familiar way. The molecules that make up proteins, DNA, and every cell in the human body rely on precise electromagnetic interactions between atoms occurring at very specific, very gentle field strengths. A magnetar's field does not gently nudge these interactions. It overwhelms them entirely. This single fact is part of why scientists describe a magnetar's vicinity as lethal, even without direct contact. It is not that you would be struck by anything. It is that the very atoms making up your body, your equipment, your ship, would begin to be physically reshaped by a field reaching out far beyond the star's visible surface. How far does this danger actually extend? Various estimates from astrophysicists, working from the known field strengths of confirmed magnetars, suggest that getting within roughly 1,000 kilometers of one would likely be fatal to a human being, primarily due to the way the field would interact with the body's own electromagnetic processes, particularly the ionic currents our nervous system relies upon. Some estimates extend that danger zone outward considerably further, depending on which biological systems are considered most vulnerable. For comparison, the distance from the surface of Earth to low orbit, where the International Space Station operates, is roughly 400 kilometers. The danger zone of a magnetar, by some estimates, would extend several times that distance. An object the size of a city, in other words, projects a kill radius that would comfortably encompass low Earth orbit and well beyond, without the magnetar needing to release a single burst of radiation. Simple proximity to the field would be enough. This is worth sitting with for a moment, because it inverts our usual intuition about danger and size. We tend to assume that bigger objects are more dangerous and smaller ones less so. A magnetar challenges that assumption directly. It is barely larger than a city, yet its zone of lethal influence could swallow a significant portion of near-Earth space. There is a particular irony embedded in this fact. A magnetar's destructive reach has nothing to do with its size, and almost everything to do with a single physical property locked into its structure at the moment of its birth. Two objects of identical mass and nearly identical size, one an ordinary neutron star and one a magnetar, could have wildly different danger profiles purely because of how their internal dynamo happened to behave during a window of perhaps 20 seconds, billions of years in the past. The danger is not limited to biology. Electronics depend on carefully controlled electric currents and the predictable behavior of charged particles within circuits. A sufficiently powerful external magnetic field can induce currents in conductive materials that were never meant to carry them, a phenomenon related to the same basic physics behind a technology called electromagnetic pulse weapons, though on a scale that makes any human-built device seem trivial by comparison. Even from many thousands of kilometers away, a magnetar's field could, according to some calculations, disrupt the operation of a credit card's magnetic strip, scramble a hard drive, or interfere with the navigation systems on a spacecraft. Closer in, that disruption escalates toward catastrophic equipment failure. Modern spacecraft electronics are typically shielded against the kind of charged particle radiation produced by our own sun's solar flares, but no spacecraft has ever been designed to withstand a static field anywhere close to magnetar strength. simply because there has never been a practical reason to consider it. This raises an unsettling thought experiment, one astrophysicists occasionally use to communicate just how extreme magnetars really are. If a magnetar somehow appeared a few hundred kilometers from Earth, replacing nothing, destroying nothing directly, simply existing there, it would not need to do anything further. The electromagnetic chaos alone would be sufficient to collapse global electronic infrastructure within seconds, before anyone could even process what was happening. Satellites would fail. Power grids, dependent on carefully balanced electrical currents, could experience catastrophic surges. The disruption would not arrive as a single, dramatic event, but as an instantaneous planet-wide failure of nearly every system that depends on controlled electromagnetism, which, in the modern world, is almost every system that matters. We will return to this thought experiment later in the documentary, because it leads somewhere important about how astronomers think about existential risks that are not asteroid impacts or supernovae, but something far less commonly discussed. For now, there is a more immediate question worth asking. If magnetars are this dangerous, simply by existing nearby, what happens when one of them becomes unstable? That question brings us to one of the most extraordinary events ever recorded in the history of astronomy. On December 27, 2004, instruments designed to monitor gamma-ray activity across the sky detected something that, for a brief moment, looked like it might be an error in the equipment. A burst of gamma radiation arrived from the direction of a known magnetar called SGR 1806-20, located roughly 50,000 light-years away on the far side of the galaxy. The burst was so intense that it saturated detectors on multiple spacecraft simultaneously. For a fraction of a second, this single magnetar, located on the opposite side of the Milky Way, was brighter in gamma rays than every other source in the observable gamma-ray sky combined. Researchers monitoring data from several different satellites that day initially suspected an instrument malfunction simply because the readings did not look like anything previously recorded from a stellar source. Detector saturation of this kind is usually associated with calibration errors, not genuine astrophysical events. It took cross-referencing data from multiple independent spacecraft, instruments built by different space agencies, using different detection technology, all recording the same anomalous spike at the same moment, before researchers became confident that this was a real signal rather than a technical glitch. To put this in perspective, the effects of this flare were detectable, not just by space-based instruments, but by ground-based monitoring stations as well. The burst was energetic enough to measurably affect the upper atmosphere of Earth, briefly altering the ionosphere in a way more commonly associated with solar flares originating from our own sun, despite the source being 50,000 light-years away rather than 93 million miles away. Some researchers have noted that the burst's effect on Earth's atmosphere was comparable to that of a moderate solar flare, an extraordinary thing to consider when the source was on the far side of the galaxy, rather than in our own solar system. The event is now understood as what astronomers call a giant flare, and it is believed to result from something happening not in the magnetar's magnetic field directly, but in its crust. Yes, a neutron star has something resembling a crust, an outer layer of densely packed matter arranged in a crystalline lattice, similar in structural principle, though wildly different in scale and composition, to the way ice forms a crystalline structure. Beneath that crust lies the super-dense interior of the star. In a magnetar, the extraordinarily powerful magnetic field is not static. It twists, stresses, and shifts the structure of the crust itself, applying mechanical strain to material that is, paradoxically, both incredibly rigid and under immense internal stress. Eventually, in events that researchers compare to a kind of stellar earthquake, the crust fractures. These events have been nicknamed starquakes, and the comparison to terrestrial earthquakes, while imperfect, captures something true about the underlying mechanism. Built-up stress, eventually released in a sudden structural failure. On Earth, tectonic plates grind against one another over years or decades, accumulating strain along fault lines until that strain exceeds the structural limit of the rock, triggering an earthquake. A magnetar's crust experiences something conceptually similar, except the stress comes not from grinding tectonic plates, but from a magnetic field of unimaginable strength, twisting the crystal lattice of the crust itself, from both outside and within. The difference in scale is almost impossible to communicate. Researchers studying the 2004 event estimated that in a fraction of a second, the flare released more energy than the Sun produces in approximately 100,000 years. Some estimates for the total energy released in the starquake event range even higher, depending on the assumptions used in the calculation. Whatever the precise figure, the conclusion is the same. In roughly the time it takes to blink, this single, small, fractured neutron star outproduced the combined output of our Sun across a span of time longer than all of recorded human civilization. Consider the comparison more carefully. Recorded human civilization, by most reckonings, spans somewhere on the order of 5,000 to 10,000 years, from the earliest writing systems to the present day. The 2004 flare, in well under a second, matched roughly 10 to 20 times that span's worth of solar energy output. Human history, in its entirety, is a rounding error against a single fracture in a faraway star's crust. It is worth pausing on the strangeness of what actually happened here. This was not a star exploding in the conventional sense. The magnetar did not blow itself apart. It was, in effect, a crack, a structural failure in the outer layer of an object roughly 12 miles across, located 50,000 light-years from Earth. And that crack alone generated enough energy to be detected instantaneously by instruments built by a species that did not yet know magnetars like this existed in any detail. This single event transformed magnetars from a theoretical curiosity discussed mostly within specialized circles of astrophysics into one of the most closely monitored categories of object in the sky. If a crack in a neutron star's crust, an event lasting a fraction of a second, could rival the most energetic phenomena known to astronomy, what did that say about objects capable of producing such fractures in the first place? This question takes us back to the unresolved mystery from Part 1. How does an object generate and sustain a magnetic field powerful enough to fracture its own crust through magnetic stress alone? We have an explanation for the field's origin: the dynamo mechanism operating in the first seconds after the star's birth. But understanding how a field forms is different from fully understanding what that field is capable of doing over the following thousands of years, and astronomers are still working through the consequences. There is also a second, quieter mystery buried inside the 2004 event, one that becomes more interesting the longer you sit with it. If this is what a magnetar, 50,000 light-years away can do to our planet's ionosphere. What would happen if a magnetar's giant flare occurred not 50,000 light-years away, but considerably closer? We are going to come back to that question. It connects directly to one of the genuine, serious areas of research within modern astrophysics: the study of nearby stellar hazards and how magnetars fit into a much larger and more sobering conversation about cosmic threats to life on Earth. The 2004 event from SGR 1806-20 was not, in fact, the first giant flare astronomers had ever recorded. It was simply the largest, and the one that arrived after the magnetar model had matured enough for researchers to interpret what they were seeing with reasonable confidence. Two earlier giant flares had already been observed, decades before, though their true nature was understood only in retrospect, once the magnetar framework existed to explain them. The first of these earlier events, recorded in March 1979 from a source in a satellite galaxy of the Milky Way, would eventually become one of the founding pieces of evidence for the entire magnetar concept, something we will examine closely in the next section. A second giant flare, somewhat less energetic than the 2004 event, was recorded in August 1998 from a different magnetar entirely, and it too briefly disrupted satellite instrumentation before fading. At the time of the 1980 event, the magnetar model had only recently been proposed and was still met with considerable skepticism within parts of the astrophysics community. The 1998 flare provided crucial supporting evidence, but it was the far larger 2004 event from SGR 1806-20 that finally removed almost all doubt. This pattern, smaller, less understood signals arriving years before the data and theory aligned well enough to make sense of them, recurs throughout the history of magnetar science, and we will see it again as we trace the discovery story back to its true beginning. But before we go further into the danger and the discovery, we need to understand magnetars more completely, because so far we have only described what magnetars do. We have not yet explored how rare they are, how they were discovered, why their existence as a category took decades for science to conform, and what their inner structure might actually look like, layer by layer, if we could somehow peer inside one. The story of how magnetars came to be understood is itself a story of scientific stubbornness, false starts, and a phenomenon that, for years, did not fit neatly into any existing category. In March 1979, instruments designed to monitor for nuclear weapons tests, originally launched as part of a Cold War-era satellite network known as the Vela program, detected an extraordinarily intense burst of gamma rays and X-rays. The burst was so powerful that it briefly disrupted the very satellites built to detect it, momentarily overwhelming their instrumentation. These satellites had originally been designed for an entirely different purpose: verifying compliance with nuclear test ban treaties by detecting the distinctive radiation signature of an atmospheric nuclear detonation. Instead, they had inadvertently become some of the most sensitive gamma-ray observatories of their era, and on this occasion, they recorded something that had nothing to do with human weapons testing at all. What made the event strange was not just its intensity. It was followed by a series of fainter, regularly repeating pulses, occurring with a period of roughly 8 seconds, fading gradually over several minutes. This pattern did not resemble the gamma-ray bursts that astronomers were beginning to catalogue from distant galaxies, which typically appeared once and never repeated. It looked like something local, something pulsing with a kind of internal rhythm, almost like a bell that had been struck once and continued to ring as it slowly quieted. This event, source SGR 052666, was eventually traced to a supernova remnant in a satellite galaxy of the Milky Way called the Large Magellanic Cloud, visible from the southern hemisphere as a faint, hazy smudge in the night sky. Researchers realized they were looking at something genuinely new, an object that periodically released enormous bursts of soft gamma rays, distinct from both the slow, predictable pulses of ordinary pulsars and the one-off, distant explosions associated with classic gamma-ray bursts. These objects came to be classified, somewhat awkwardly, as soft gamma repeaters, abbreviated SGRs, a category defined essentially by what they did rather than by any settled theory of what they were. For more than a decade following their discovery, the underlying physics of soft gamma repeaters remained genuinely unresolved. Were they unusual black holes, strange binary systems, perhaps a neutron star feeding off the material of a companion star, a new type of neutron star entirely? Nobody could say with confidence. Several competing models circulated through the astrophysics community during the 1980s, each attempting to account for the repeating, decaying burst pattern, and each falling short of explaining the full range of observed behavior. The conceptual key that eventually unlocked the mystery came from theoretical work in the early 1990s, particularly from astrophysicists Robert Duncan and Christopher Thompson, who proposed that certain neutron stars could, under specific formation conditions, develop magnetic fields vastly more powerful than anything previously considered plausible for such objects. Their theoretical models, published in a series of papers beginning in 1992, suggested these ultramagnetized neutron stars, which they termed magnetars, could explain the behavior observed in soft gamma repeaters and could account for the enormous sporadic bursts of energy these objects periodically released. This was in the early 1990s, a fairly bold theoretical claim. It required field strengths that strained credulity, given what was understood at the time about the upper limits of neutron star magnetism. The theory essentially proposed that nature was capable of generating magnetic fields 1,000 times stronger than anything observed in ordinary pulsars, fields so extreme that they would, by themselves, become the dominant source of the star's observed behavior, more influential than even the star's own rotation in determining how it released energy. Within the astrophysics community at the time, this represented a genuine departure from the conventional understanding of neutron star physics, and like many bold theoretical proposals, it was initially met with a mixture of interest and skepticism. It took several more years of accumulating observational evidence, comparing predicted behaviors against what telescopes were actually recording, before the magnetar model gained broad acceptance within the astrophysics community. Key supporting evidence arrived gradually throughout the 1990s, including measurements of the spin-down rates of known soft gamma repeaters, the rate at which their rotation gradually slows over time, which matched what the magnetar model predicted far better than competing explanations. The 2004 giant flare from SGR 1806-20, which we examined in the previous section, arrived roughly a decade after the theoretical framework had become reasonably well established and served as one of the most dramatic confirmations of just how extreme these objects could be in practice. Something worth pausing on here, beyond the specific history of magnetars. This discovery illustrates something important about how science often actually progresses, not through a single triumphant breakthrough, but through decades of accumulated, partially understood anomalies, slowly converging toward an explanation that initially seemed almost too extreme to be taken seriously. For more than 10 years, instruments were recording behavior from these objects that did not fit comfortably into existing categories. The data existed. The puzzle existed. What was missing, for over a decade, was a theoretical framework extreme enough to actually account for what was being observed. When that framework finally arrived, it did not simply explain a handful of strange signals. It opened an entirely new category of stellar object, one that forced astronomers to revise their understanding of just how powerful a magnetic field, generated by natural processes, could actually become. This raises a deeper question worth carrying forward through the rest of this documentary. If magnetars existed, in some sense, for decades before anyone had a theoretical model capable of explaining them, what other extreme phenomena might currently be sitting in astronomical data, recorded but not yet understood, simply waiting for the right theoretical breakthrough to make sense of them? We do not have an answer to that question. Nobody does, by definition, but it is worth holding on to as we continue, because it reframes magnetars not simply as an unusual category of star, but as a recent reminder of how much of the universe's most extreme behavior may still be hiding in plain sight, recorded by instruments, but unexplained by theory. As of current astronomical catalogues, only a relatively small number of confirmed magnetars are known, generally cited as somewhere around 30 confirmed objects, though the number shifts slightly as new candidates are identified and confirmed or ruled out. This is an extraordinarily small population compared to the broader category of neutron stars, of which thousands have been catalogued, and a vanishingly small fraction compared to the estimated total population of neutron stars believed to exist throughout the Milky Way. A number that may run into the hundreds of millions, the vast majority of which are simply too old, too cold, or too faint to detect with current instruments. This scarcity itself is a mystery worth sitting with. If magnetars require a very particular, narrow set of birth conditions, as the dynamo theory from Part 1 suggests, then their rarity might simply reflect how rarely those conditions occur during a star's collapse. But there is another possibility that some researchers have considered. Magnetars might not be intrinsically rare so much as short-lived, at least in terms of how long they remain detectable as magnetars. This leads into one of the more genuinely unresolved areas of magnetar science: the question of how a magnetar's intense magnetic field evolves over time, and what a magnetar eventually becomes once that field begins to decay. That question deserves its own careful exploration, because it touches on something central to understanding these objects. Magnetars may not be a permanent category of star at all. They may be a temporary, violent phase that certain neutron stars pass through before settling into something quieter and far less studied as a result, simply because it no longer announces itself with bursts of gamma radiation. We will explore that idea, along with the internal structure of a magnetar, the physics of starquakes in more detail, and the unresolved question of what exactly lies beneath a magnetar's crust in the next part of this documentary. But there is something else worth addressing first, something that the 2004 flare quietly raised. And that deserves direct, honest treatment rather than implication. Just how seriously should we actually take the idea of a magnetar as a threat to Earth? Is this genuine scientific concern, or simply a dramatic framing applied to an object that, in practice, poses no realistic danger to us at all? The honest answer, as we will see, lies somewhere between those two extremes. And getting it right requires understanding both the real physics of risk and the actual distances involved. This is where scientific honesty becomes essential, because it would be easy, at this point in the documentary, to let the dramatic framing of most dangerous star in existence drift into something closer to fear-mongering. That is not the goal here. The goal is to take the actual physics seriously and let the real numbers tell us how concerned we should be. The closest confirmed magnetars to Earth are located thousands of light-years away, SGR 1806-20. The source of the 2004 giant flare sits at a distance of roughly 50,000 light-years, far across the galaxy. Other known magnetars are scattered at similarly vast distances, generally located within the plane of the Milky Way, often associated with regions of recent massive star formation, which makes sense given that magnetars are the remnants of massive stars. One of the nearer known examples, a magnetar called SGR 1900+14, sits at a comparable distance of around 20,000 light-years, itself the source of a notable, though less extreme, giant flare recorded in August 1998. At these distances, even the most energetic giant flare on record posed no meaningful danger to Earth. The 2004 event measurably affected our planet's ionosphere, a genuinely remarkable thing for a source 50,000 light-years away to accomplish. But it did not pose any threat to human health, technology, or the biosphere. The danger zone we discussed in Part 2, the 1,000-kilometer radius of potentially lethal magnetic field effects, applies to proximity to the magnetar itself, not to its radiation reaching us across the galaxy. For a magnetar to pose a serious, direct threat to Earth, it would need to be vastly closer than any known magnetar currently is, likely within a few dozen light-years at most, for even a giant flare's gamma-ray burst to pose a meaningful radiation hazard to our atmosphere and ozone layer. And within a tiny fraction of that distance, measured in mere thousands of kilometers rather than light-years, for the kind of direct magnetic field effects discussed earlier to become relevant. No known magnetar exists anywhere close to those distances. The nearest magnetars sit tens of thousands of light-years away, a distance so vast that it is genuinely difficult to put in relatable terms. Light leaving one of these magnetars today would not arrive at Earth until long after every currently living human being, and likely many subsequent generations, had lived and died. The honest answer involves a branch of astrophysics dedicated to cataloging and assessing low-probability, high-consequence cosmic events, the same broad category of research that considers gamma-ray bursts, nearby supernovae, and asteroid impacts. Magnetars, and the giant flares they occasionally produce, are included in this conversation not because any specific known magnetar poses a current threat, but because the category of object itself represents a kind of cosmic hazard that traditional risk assessments, historically focused on asteroids and comets, had not fully accounted for until relatively recently. Some researchers have explored as a theoretical exercise rather than an active concern. What would happen if a magnetar's giant flare occurred within a few thousand light-years of Earth, a distance still vastly larger than any known magnetar's actual location, but close enough that the gamma-ray pulse could plausibly damage the ozone layer, similar to concerns raised about nearby gamma-ray bursts more broadly? Some of this research has even speculated, cautiously and without strong consensus, about whether a sufficiently close giant flare in the deep past might have contributed to one of Earth's prehistoric mass extinction events, an idea that remains firmly speculative and far from established, but illustrates the kind of careful, hypothetical thinking this branch of astrophysics engages in. This remains a hypothetical scenario explored to understand the physics of risk, not a forecast of anything expected to occur. What makes magnetars worth taking seriously, scientifically, is not that one is about to threaten Earth. None is. It is that magnetars represent a category of object capable of releasing energy at scales that strain our existing understanding of physics, located throughout the galaxy, in numbers we have only begun to properly catalogue, behaving in ways that were entirely unanticipated by theory until astonishingly recently in the history of astronomy. This raises the genuinely open question that will carry us through the remainder of this documentary. If an object this extreme could remain almost entirely unexplained until the 1990s, what does that tell us about the limits of our current physics? Are magnetars simply an unusually dramatic application of magnetic field physics we already understand? Or are they hinting at something more fundamental that we have not yet fully grasped? Something about how matter behaves at densities and field strengths that cannot currently be replicated or tested anywhere on Earth. To explore that question properly, we need to go inside a magnetar. We need to understand, as best current physics allows, what its crust is actually made of, what lies beneath that crust, and why some researchers suspect that the interior of a magnetar might be one of the strangest states of matter permitted to exist anywhere in the universe. That exploration, along with the deeper physics of starquakes, the eventual fate of magnetars as they age, and what magnetars reveal about the outer boundaries of known physics, will form the next major movement of this documentary. We have spent considerable time discussing what a magnetar's magnetic field does to the world around it. Now we need to turn inward and ask a question that takes us into some of the strangest physics in modern astronomy. What is a magnetar actually made of, layer by layer? From its outer surface down to whatever lies at its center. This is not an idle curiosity. Understanding the interior structure of a magnetar is essential to understanding the starquakes we discussed earlier. And it turns out to be one of the genuine frontiers of theoretical physics, a place where our equations begin to strain against the limits of what we can verify. No laboratory on Earth, no particle accelerator, no experimental apparatus we have ever built can recreate the conditions found even a few feet beneath a magnetar's surface. Everything we know about its interior comes from indirect evidence. The way the star spins, the way its rotation gradually slows, the precise timing of its bursts, and careful theoretical modeling built on the foundations of nuclear physics extended into territory no experiment can directly confirm. If you could approach a magnetar safely, which you cannot, the first thing you would encounter is a thin layer of plasma, sometimes loosely called the star's atmosphere. though it bears almost no resemblance to the atmosphere of a planet or even an ordinary star. This layer is only a few centimeters thick, composed of extremely hot, magnetized plasma. Because of the intensity of the magnetic field, the atoms within this layer are distorted into the elongated shapes we discussed earlier, and the entire layer behaves less like a gas and more like a strange, magnetically constrained fluid, with particles forced to move along the field lines rather than freely in any direction. This thin plasma layer sits atop something far more solid, the crust. Below that thin atmospheric layer lies the outer crust, and this is where the story becomes genuinely fascinating. The outer crust of a neutron star, magnetar or otherwise, is believed to be composed of atomic nuclei arranged in a rigid lattice structure, not unlike the way atoms arrange themselves in a crystal, but compressed to densities that have no equivalent anywhere else in the observable universe. As you descend through the outer crust, the nuclei become increasingly exotic. Near the very top, the material resembles iron, the heaviest element typically produced in the final stages of a massive star's life before collapse. Moving deeper, the immense pressure forces nuclei into increasingly neutron-rich configurations, types of atomic nuclei that would be wildly unstable and impossible to produce or to sustain under any condition found on Earth, but which remain stable here, held together by pressure, rather than by the ordinary nuclear forces that govern chemistry in a laboratory. As you move deeper into the crust, the density increases enormously, and the physics shifts. In the inner crust, nuclei become so densely packed that some neutrons begin to leak out of them entirely, forming what physicists call a neutron superfluid, a state of matter that flows with effectively zero viscosity, behaving in ways that are difficult to intuit from everyday experience with fluids. A superfluid, once set into motion, will continue flowing indefinitely without ever slowing down from friction, a property so counterintuitive that even physicists who study it regularly describe it as one of the strangest accessible states of matter in nature, accessible here only because the conditions inside a neutron star happen to recreate, on a vastly larger scale, the same quantum effects that researchers achieve briefly in laboratories using temperatures near absolute zero. This crust is not the soft, brittle material the word might suggest. Calculations suggest that neutron star crust material may be among the strongest materials permitted to exist under known physics, some estimates suggesting it could be tens of billions of times stronger than steel, in terms of the stress required to deform or fracture it. To put this in perspective, steel itself is considered remarkably strong by ordinary engineering standards, used to build bridges, skyscrapers, and the hulls of ships specifically, because of its resistance to deformation. Neutron star crust material occupies a category of strength so far beyond steel that the comparison almost becomes meaningless, the way comparing the distance to the corner store with the distance to a neighboring galaxy becomes meaningless, even though both are technically distances. And this is precisely what makes the starquakes we discussed in Part 3 so remarkable. The magnetic field within a magnetar is strong enough to apply mechanical stress to a material believed to be among the strongest substances permitted in the universe, and strong enough, eventually, to fracture it. This is not a small thing. It tells us that the magnetic stresses inside a magnetar's crust are operating at a scale that very few other phenomena in the cosmos can match. Beneath the crust lies the core, and here our understanding becomes considerably less certain. The outer core is believed to consist primarily of neutrons, along with smaller populations of protons and electrons, all existing in a superfluid and superconducting state, exotic quantum phenomena that, on Earth, we typically only achieve briefly, under extreme laboratory conditions involving temperatures near absolute zero. Inside a neutron star, similar quantum states may exist naturally, sustained not by cold, but by the sheer crushing density of the material. This detail matters more than it might first appear, because a superconductor behaves very differently from ordinary matter when placed inside a magnetic field. A superconductor tends to expel magnetic field lines from its interior, a phenomenon called the Meissner effect, well documented in laboratory superconductors on Earth. If the interior of a neutron star is genuinely superconducting, the magnetic field threading through it would not simply pass through uniformly. It would instead become confined into countless thin filaments, sometimes called flux tubes, each one carrying an enormous concentration of magnetic energy woven through the superfluid neutron material like threads through fabric. The interaction between these flux tubes and the rotating, flowing superfluid around them is believed to play a significant role in some of the more subtle behaviors magnetars display, including small, sudden changes in their rotation rate that researchers call glitches, something we will return to shortly. The inner core is where theoretical physics becomes genuinely speculative. Some models suggest that, at the very center of a neutron star, densities may become so extreme that neutrons themselves break down into their constituent quarks, the fundamental particles that make up protons and neutrons, forming a theoretical state of matter called quark matter, or in some proposed models, a more exotic substance researchers have termed strange matter, named for the inclusion of a particular type of quark, called the strange quark, that does not typically appear in ordinary matter under everyday conditions. No one has confirmed this happens. It remains one of the genuinely open questions in nuclear astrophysics. And magnetars, because of their extreme magnetic environment, layered on top of an already extreme density, may offer a unique natural laboratory for eventually testing these ideas. Assuming we can ever develop instruments precise enough to probe conditions we will never be able to replicate on Earth, researchers studying this question often rely on a tool called the equation of state, a mathematical relationship describing how matter behaves under given pressure and density conditions. Different theoretical models of the neutron star interior predict different equations of state, and one of the more promising ways to distinguish between competing models involves precisely measuring the masses and radii of real neutron stars, then checking which theoretical equation of state best matches the observed properties. This has become an active area of research using a combination of telescope observations and, more recently, gravitational wave detections from neutron star collisions, an entirely separate avenue of evidence that did not exist as a practical research tool until relatively recently in the history of astronomy. Here is something that separates a magnetar from an ordinary magnet in an important way. The magnetic field of a magnetar is not confined to the surface or the outer layers. Current theoretical models suggest that an internal magnetic field, potentially even stronger than the field we can measure at the surface, may exist deep within the star, twisted and wound through the superconducting interior. This internal field is believed to be central to how starquakes occur. As the internal field evolves and shifts over time, perhaps over years or decades, it places mounting stress on the rigid crust above it from underneath, in addition to whatever external stresses the surface field experiences. Eventually, something has to give. The crust fractures, and energy that may have been building for years is released in a fraction of a second, in the kind of giant flare we examined from 2004. This raises a fascinating and still unresolved question, one that researchers are actively working to model. How exactly does energy stored in a deeply buried magnetic field translate into the kind of crust fracture and subsequent gamma-ray flare we actually observe? The basic outline is understood, the precise mechanism in full mathematical detail, connecting internal fields' slow evolution to the sudden, violent release of energy, remains an active area of research, refined as each new observed flare provides additional data to test against theoretical models. Beyond the dramatic giant flares, magnetars display a range of subtler, but still genuinely puzzling behaviors that offer additional clues about their interior structure. Most neutron stars, including magnetars, gradually slow their rotation over time, losing rotational energy primarily through the electromagnetic radiation their spinning magnetic field generates. This slowdown is generally smooth and predictable. Occasionally, however, a neutron star will suddenly speed up just slightly in an event called a glitch, before resuming its gradual slowdown. This is believed to result from the interior superfluid, which does not necessarily rotate at exactly the same rate as the solid crust above it, suddenly transferring angular momentum to the crust, like an internal flywheel briefly synchronizing with the structure surrounding it. Glitches have been observed in ordinary pulsars for decades and are reasonably well understood within the broader framework of neutron star interior physics. Magnetars, however, occasionally display the opposite behavior, a sudden, unexpected slowdown rather than a speed up, an event researchers have termed an antiglitch. Antiglitches are considerably rarer and less well understood than ordinary glitches, and they may be connected to the same kind of internal magnetic stress that produces starquakes, though the precise relationship remains an active subject of study. Each newly observed glitch or antiglitch provides another small data point that theorists can use to refine their models of what is actually happening beneath a magnetar's crust, deep in a region we will likely never observe by any means other than its subtle effects on the star's rotation. Perhaps the strangest realization to take from this section is that a magnetar is not a static object, simply sitting in space, holding a powerful magnetic field. It is, in a sense, a star perpetually in the process of slowly destroying its own structure from the inside. The magnetic field that defines what a magnetar is, the very feature that makes it scientifically remarkable, is also the mechanism by which the star repeatedly fractures itself. This is not a flaw in the system. It is the system. A magnetar's defining feature and its primary mechanism of self-destruction are the same physical structure, viewed at different timescales. This naturally raises the next question we need to address. If a magnetar is continuously placing stress on itself and periodically fracturing, what is the long-term outcome of this process? Does a magnetar simply continue indefinitely, fracturing every so often for the rest of its existence? Or does this process have an endpoint, a moment when the magnetar stops being a magnetar at all? That question takes us into the life cycle of these objects and into one of the more genuinely surprising findings of recent magnetar research. Magnetars do not remain magnetars forever. Understanding why requires looking at what happens to their magnetic field over time. And the answer acts back to something we touched on earlier: the surprisingly small number of confirmed magnetars currently catalogued. A magnetar's extraordinary magnetic field, generated in the first violent seconds after the star's formation, does not remain at constant strength indefinitely. Over time, on the order of roughly 10,000 years, theoretical models suggest the field gradually weakens, as the internal currents sustaining it slowly dissipate, converting magnetic energy into heat and radiation. This decay process is itself believed to be a significant source of the star's overall energy output during this period, sometimes called magnetic field decay heating, and it may help explain why many magnetars are observed to be unusually hot for their age, compared to ordinary neutron stars of similar age that lack such an intense field to decay. 10,000 years sounds, by human standards, like an extraordinarily long time. On a cosmic timescale, particularly compared to the billions of years over which an ordinary star like the Sun will live and eventually die, it is a remarkably brief window. This suggests that the magnetar phase, the period during which an object behaves in the dramatic gamma-ray flaring manner we have spent this documentary exploring, may represent only a relatively short chapter in the much longer life of a neutron star. This directly addresses the puzzle we raised earlier about why so few magnetars have been catalogued. It may not be that magnetars are an inherently rare outcome of stellar collapse. It may be that magnetars are not rare to form, but rare to catch, because the window during which a neutron star actively displays magnetar-like behavior, the giant flares, the soft gamma repeater activity, may only last for a small fraction of the object's overall existence. If this picture is correct, then a magnetar, after its field has sufficiently decayed, would eventually settle into something closer to an ordinary, quiet neutron star. Still incredibly dense, still spinning, but no longer producing the dramatic bursts of energy that originally identified it as a magnetar. This raises a quietly unsettling thought. If magnetars eventually fade into ordinary, undetectable neutron stars, then the population of neutron stars, currently catalogued as ordinary, might include a meaningful number of former magnetars, objects that once, in the relatively recent cosmic past, were capable of producing some of the most energetic events known to astronomy, now sitting quietly in the dark, indistinguishable from neutron stars that never went through that phase at all. In other words, some of the seemingly unremarkable neutron stars currently scattered throughout our galaxy may be retired monsters. There is at present no definitive way to identify which ones, if any, fall into this category, though researchers studying the demographics and ages of neutron star populations continue working on methods that might eventually distinguish them. Some researchers have proposed examining subtle compositional or structural signatures left behind by a now decayed extreme magnetic field, comparing the surface temperature and cooling history of a candidate neutron star against what would be expected if it had once carried a magnetar strength field early in its life. This remains a developing area of research rather than a settled methodology. It is worth being honest here about something that remains scientifically unsettled. Researchers do not yet fully agree on whether all magnetars eventually fade in this manner, whether some retain enough magnetic field strength to remain active far longer than 10,000 years, or whether the relationship between a neutron star's birth conditions and its long-term magnetic evolution is even consistent across the broader population. Some models suggest considerable variation is possible, depending on factors like the exact strength of the initial field and the internal composition of the star. This honesty matters, because it would be easy to present the 10,000-year decay timescale as a settled fact rather than what it actually is. A well-supported but still actively researched theoretical estimate, refined as observational data from known magnetars, some of which have now been monitored for several decades, continues to accumulate. A small number of known magnetars are estimated, based on their association with nearby supernova remnants of known age, to be remarkably young by astronomical standards. In some cases, less than a few thousand years old, essentially newborns by cosmic measure. Studying these younger examples in detail, comparing their behavior to older magnetars, believed to be closer to the end of their active phase, provides one of the more direct ways researchers can test predictions about how the magnetar phase evolves over time. There is a relatively recent development in astronomy that has added an entirely new dimension to magnetar research, one that did not exist when the dynamo theory was first proposed in the early 1990s. The discovery of fast radio bursts, extraordinarily brief, intensely powerful pulses of radio waves, lasting only milliseconds, arriving from sources scattered across the universe, many originating from galaxies billions of light-years away. The first fast radio burst was identified in archival data in 2007, found within older radio telescope observations rather than detected live, and for years afterward, these signals remained one of astronomy's most puzzling unsolved mysteries. Short, energetic, and seemingly impossible to trace back to a specific cause. The challenge was compounded by the nature of the bursts themselves, lasting only a few milliseconds and arriving unpredictably from seemingly random points across the sky. Fast radio bursts were exceptionally difficult to catch in the act, and even more difficult to trace back to a precise point of origin once detected, since most early radio telescopes lacked the resolution to pinpoint exactly which galaxy, let alone which specific object within that galaxy, had produced the signal. The development of new radio telescope arrays, specifically designed to monitor wide areas of sky continuously, most notably an instrument called CHIME, based in Canada, dramatically increased the rate at which fast radio bursts could be detected, transforming the field from one in which only a handful of bursts had ever been recorded to one in which researchers began cataloging hundreds and eventually thousands of individual events. This explosion of available data revealed that fast radio bursts came in at least two broad categories. The vast majority appeared to be one-time events, never repeating from the same location, while a smaller subset displayed repeating behavior, firing multiple bursts from the same source over time, a crucial clue that would eventually connect directly back to magnetars. Then, in April 2020, something remarkable happened. A fast radio burst was detected originating from within our own galaxy, traced to a known magnetar called SGR 1935 plus 2154, accompanied simultaneously by a burst of X-rays. The detection came from the very same CHIME telescope array that had been transforming fast radio burst research more broadly, working in coordination with other observatories that confirmed the simultaneous X-ray counterpart, providing the kind of multi-instrument confirmation that had similarly been essential to confirming the 2004 giant flare years earlier. This was the first time a fast radio burst had been directly linked to a specific, identifiable source, and that source was a magnetar. The discovery did not resolve the entire fast radio burst mystery. Many fast radio bursts originate from distances and under circumstances that suggest other mechanisms may also be at play, and the broader population of fast radio bursts likely has more than one explanation, particularly the most distant and energetic examples, which may require different or additional physical processes beyond what a single galactic magnetar event could produce. But it firmly established that at least some, and possibly a significant fraction, of fast radio bursts originate from exactly the kind of object we have spent this documentary exploring. This finding transformed magnetars from a fascinating but somewhat isolated category of extreme stellar object into a potential key to one of the broader unsolved mysteries of modern astrophysics. The hidden question, buried inside fast radio burst research, in many cases may turn out to be a question we have already been quietly exploring throughout this documentary. What exactly happens when a magnetar's crust fractures? And how does that fracture translate into the specific signatures, gamma rays in some cases, radio waves in others, that we detect from across the galaxy? Or, in the case of more distant fast radio bursts, potentially from across the universe? Researchers have proposed several specific mechanisms attempting to explain exactly a magnetar might generate a fast radio burst, including models involving the sudden snapping and reconnection of twisted magnetic field lines high above the star's surface, and models involving disturbances propagating through the star's magnetosphere following a starquake deep within the crust. These models remain under active investigation and refinement, each one tested against the growing catalogue of observed events in a process not unlike the decade-long effort that originally established the magnetar model itself in the 1990s. We have spent this documentary moving from the formation of magnetars, through their dangerous magnetic fields, through the 2004 giant flare, into their interior structure, and finally into their long-term evolution and connection to fast radio bursts. It is worth pausing now to zoom out and ask a larger question. Why do physicists outside the narrow specialty of neutron star research pay close attention to magnetars at all? One of the most valuable aspects of magnetars, from a physics research perspective, is that they provide a natural laboratory for studying conditions that cannot be replicated anywhere on Earth, regardless of how advanced our technology becomes. The strongest sustained magnetic fields ever produced in a laboratory setting on Earth, achieved briefly using specialized equipment, are measured in the tens of Teslas. Technically impressive by human engineering standards, but trivial compared to the fields found at a magnetar's surface, which exceed laboratory fields by many orders of magnitude. This matters because certain predictions of fundamental physics, particularly within quantum electrodynamics, the theory describing how light and matter interact at the quantum level, becomes significant only under field strengths far beyond anything achievable in a laboratory. One such prediction involves a phenomenon called vacuum birefringence, the idea that an extremely powerful magnetic field can alter the properties of seemingly empty space itself, changing the way light polarizes as it passes through. Several research teams analyzing light from known magnetars have reported observations consistent with this prediction, suggesting that even the vacuum of space, the supposedly empty backdrop of the universe, behaves differently in the presence of a field this extreme. If confirmed through further observation, this would represent direct evidence for a genuinely strange prediction of quantum physics, one that has remained essentially untestable since it was first proposed roughly a century ago, made testable only because magnetars happen to exist and happen to be observable from Earth. This is part of why magnetars matter to physicists who have no particular interest in neutron stars themselves. These objects function as a kind of natural particle accelerator and laboratory, conducting experiments at scales and intensities that human civilization, with all of its current technology, simply cannot replicate. There is something quietly remarkable in this. Some of the most advanced facilities ever constructed by human civilization, enormous particle accelerators built at extraordinary cost, employing thousands of researchers and engineers, exist specifically to prove physics at the smallest and most extreme scales we can reach. And yet, 50,000 light-years away, a small, dim, otherwise unremarkable dead star is quietly running an experiment our most advanced facilities cannot come close to matching, simply as a natural consequence of its own physical structure, with no purpose or intention behind it at all. Throughout this documentary, we have circled around one persistent, unresolved question. How does nature generate a magnetic field this powerful in the first place, and sustain it for thousands of years, through a mechanism we can describe in outline, but have not yet modeled with complete precision? The dynamo theory from Part 1 gives us a framework. Rapid rotation combined with violent internal convection, occurring within the first seconds after a massive star's core collapses, can amplify a magnetic field to extraordinary levels. But the precise conditions required, why some collapsing cores produce magnetars and the vast majority do not, remain only partially understood. Current research, drawing on increasingly sophisticated computer simulations of supernova core collapse, continues working toward a more complete answer, but a fully predictive model, one that could look at a given collapsing star and confidently say whether it will produce an ordinary neutron star or a magnetar, does not yet exist. These simulations represent some of the most computationally demanding calculations in all of astrophysics, requiring researchers to model the behavior of matter under conditions of extreme density, temperature, and magnetic field strength simultaneously, all unfolding over a span of mere seconds. Using some of the most powerful supercomputing resources currently available. Even with these resources, fully three-dimensional simulations of the dynamo process remain at the edge of what is currently computationally feasible, and researchers continue refining their models as computing power increases and as more observational data from confirmed magnetars becomes available to test their predictions against. This is, in its own way, one of the more humbling aspects of modern astrophysics. We have detected and characterized roughly 30 of these objects, We understand, in broad strokes, how they form, what they are made of, why they fracture, and how they eventually fade. And yet, the precise physics governing the birth of a magnetar's defining feature, the mechanism by which a stellar collapse occasionally produces a field strong enough to bend atoms and crack neutron star crust, remains an active frontier of research rather than a settled chapter in a textbook. There is a broader lesson embedded in the story of magnetars, one that extends beyond the specific physics of neutron stars. For decades, soft gamma repeaters were observed, recorded, and catalogued without anyone having a theoretical framework extreme enough to explain them. The data existed before the explanation did. It took a willingness among certain researchers to propose field strengths that initially seemed implausible. Given the conventional understanding of neutron star physics at the time, before the puzzle pieces fell into place, this pattern, observation outpacing theoretical explanation, is not unique to magnetars. It may be worth considering. As a closing thought for this section, how many other genuinely strange phenomena currently sit in astronomical archives, recorded by instruments over the past several decades, waiting for a theoretical breakthrough as bold as the one Duncan and Thompson proposed in the early 1990s, before anyone fully understands what they represent. We have spent most of this documentary at extraordinary distances, examining objects 50,000 light-years away, peering into densities and field strengths that have no equivalent on Earth. It is worth, before concluding, bringing the story back closer to something more immediately human, because that is ultimately where the significance of magnetars resides. Human beings evolved to navigate a fairly narrow range of physical conditions. Moderate temperatures, moderate gravity, moderate magnetic fields so weak we barely register their existence except through a compass needle. Almost everything about daily human experience operates within a tiny slice of the conditions that the universe is actually capable of producing. Magnetars are a vivid reminder of just how narrow that slice really is. 12 miles across, spinning in the dark, holding a magnetic field capable of bending the shape of an atom and fracturing material stronger than steel by a factor of billions. There is nothing in ordinary human experience that prepares the mind to intuitively grasp an object like this. We can describe it mathematically. We can detect its effects from across the galaxy. But truly imagining what it would be like to stand near one, if such a thing were even conceptually possible, stretches the limits of human imagination, past its breaking point. Consider, for a moment, the strange asymmetry at the heart of this entire subject. The same physical universe that produced the gentle, stable conditions, allowing complex life to evolve on Earth. Conditions calm enough for chemistry, biology, and eventually consciousness to take hold, also produces, elsewhere within that same universe, objects so extreme that they would unmake the very chemistry life depends on, simply by existing nearby. Both outcomes follow from the same underlying physical laws. The universe does not distinguish between gentle and violent. It simply allows whatever the equations permit, scattered unevenly across an almost incomprehensibly vast cosmos, with quiet, life-bearing worlds and silent, atom-bending stellar remnants existing side by side within the same galaxy, separated only by distance. There is a quieter, more reflective point worth drawing out here, one that connects to the honest risk assessment from Part 5. For most of human history, our species understood almost nothing about magnetars, soft gamma repeaters, or the physics of neutron star crusts. These objects existed throughout that entire history, scattered across our galaxy, occasionally flaring with energy that would have been detectable, in principle, by sufficiently advanced instruments had any existed. The fact that we now understand even this much about magnetars, having identified them, traced their formation, witnessed their giant flares, and connected them to entirely separate mysteries like fast radio bursts, represents a remarkably recent achievement in the long history of human curiosity about the sky. The soft gamma repeaters, detected in 1979, sat unexplained for over a decade. The theoretical framework that finally explained them is barely 3 decades old, and the connection to fast radio bursts is less than a handful of years old at the time of this documentary. This is worth holding on to. Our understanding of one of the most extreme categories of object in the known universe is, in the broader timeline of scientific knowledge, almost brand new. We are not looking at a settled chapter of astrophysics. We are looking at an active, unfolding area of discovery, one where new data continues to refine and occasionally challenge what researchers thought they understood. Every few years, it seems, a new observation arrives that adds another layer to the picture. A new giant flare, a new fast radio burst, traced to a galactic source, a new measurement hinting at exotic interior physics. The story of magnetars is, quite literally, still being written in something close to real time by researchers currently working at observatories around the world and in orbit above it. It is worth pausing to acknowledge something easily overlooked in a documentary focused on the objects themselves. None of this story would exist without an enormous, sustained, decades-long investment in building and maintaining the instruments capable of detecting these signals in the first place. The Veta satellites that stumbled upon the 1979 event were never designed with magnetars in mind. The gamma-ray observatories that recorded the 2004 giant flare were the product of careful engineering, international cooperation, and years of planning before launch. The CHIME telescope array that helped trace a fast radio burst back to a specific galactic magnetar in 2020 represents a newer generation of instrumentation designed specifically to monitor enormous swaths of sky continuously, built in anticipation of discoveries that at the time of its design had not yet been made. This is true of nearly every major discovery covered in this documentary. The universe does not announce its secrets. It requires patient, sustained human effort, often spanning entire careers, often requiring instruments built years or decades before the discoveries they eventually enable, before those secrets become visible at all. Magnetars existed throughout the entire history of human civilization, fracturing, flaring, and fading in the darkness, completely unnoticed until a specific combination of theoretical insight and technological capability finally allowed us to see them for what they are. We opened this documentary by asking why magnetars are considered, by many physicists, more dangerous than supernovae or black holes in certain respects. We have now seen the answer in detail, not because they are larger or more energetic in some absolute sense, but because their danger operates through a mechanism, an intense magnetic field reaching outward across enormous distances, that does not require proximity, impact, or direct radiation exposure in the way other cosmic hazards typically do. Simple existence nearby would be sufficient. We have also seen, through honest examination of the actual distances involved, that no magnetar currently poses any realistic threat to Earth, and that the nearest known example sits safely tens of thousands of light years away. The danger magnetars represent is real, in the sense that the physics is genuinely as extreme as described. But it is not an active or developing threat to our planet, now or in any foreseeable future. What remains, after acknowledging both of these things, the genuine extremity of magnetar physics and the genuine safety of our current cosmic neighborhood, is something more interesting than fear. It is a kind of expanded sense of what the universe is actually capable of producing, scattered throughout our galaxy in small numbers, hiding in plain sight for decades before theoretical physics caught up to what observational instruments had already recorded. A magnetar does not look impressive. Through any telescope, it would appear as little more than a faint, undistinguished point of light, smaller and dimmer than countless ordinary stars surrounding it. There is no visual cue, no obvious signal that would tell an observer they were looking at one of the most extreme objects known to exist, an object capable of bending atoms, fracturing materials stronger than steel, and briefly outshining the rest of the gamma-ray sky combined. This, perhaps, is the most lasting realization this documentary leaves behind. The universe does not announce its most extreme phenomena with obvious visual drama. Some of its most violent, most physics-defying objects sit quietly, indistinguishable, at a glance from far more ordinary stars, revealing their true nature only to instruments capable of detecting the right wavelengths. At exactly the right moment, 50,000 light years away, we now understand, in considerable detail, how magnetars form, what makes them dangerous, why their crusts fracture, what they eventually become, and how they connect to one of astronomy's more recent mysteries, in the form of fast radio bursts. But the deeper question, how a stellar collapse occasionally produces a field this extreme, and what other phenomena throughout the galaxy might be waiting for their own theoretical breakthrough, remains unresolved. Somewhere out there, scattered through the Milky Way, in numbers we have only begun to properly count, these quiet, fractured, magnetically violent stellar remnants continue spinning in the dark, slowly losing the very feature that makes them remarkable, fading over thousands of years back into the ordinary darkness, from which, in a sense, they briefly and violently emerged. That is what it means to call a star dangerous without it ever needing to explode. Before any giant flare reaches the surface of a magnetar, before any starquake sends a shockwave rippling through the crust, the violence begins in a region that is not even part of the star itself. It begins in the magnetosphere, the vast region of space surrounding the magnetar that is dominated and controlled by its magnetic field, a region so extreme and so strange that it operates by physics that barely resemble anything we encounter in ordinary life. Every magnetized object, from a kitchen refrigerator magnet to our own planet, possesses a magnetosphere of some kind. The magnetosphere is simply the region around an object where its magnetic field is the dominant influence on the behavior of charged particles. Earth has one. Jupiter has one, impressively large by planetary standards. The Sun has one. But the magnetosphere of a magnetar occupies an entirely different order of existence from any of these. In an ordinary pulsar, the magnetosphere is already a violent place. Charged particles are accelerated to near the speed of light, along the magnetic field lines, and where these accelerated particles emit radiation in the right geometry relative to Earth, we observe the characteristic pulsing we have already discussed. The physics is complex, but it follows from well-understood principles of electromagnetism, pushed into an extreme but still tractable regime. A magnetar's magnetosphere goes considerably further. The field is not simply strong, it is twisted. Over time, as the star's internal field evolves and shifts, the external field lines become wound and tangled, rather than remaining in the smooth, ordered configuration of an ordinary dipole magnet. This twisting concentrates electric currents within the magnetosphere and drives the continued acceleration of charged particles to even greater energies than would be expected from the field strength alone. It is this twisted, current-laden magnetosphere that is believed to produce much of the persistent X-ray emission that makes magnetars detectable even during the quieter periods between giant flares. The twisting also plays a central role in how the energy builds toward a catastrophic release. As the internal magnetic field shifts, applying stress to the crust from below, it simultaneously continues winding the external field lines above. Eventually, the two processes, the internal stress on the crust and the external winding of field lines, can combine to trigger a sudden, violent restructuring. The crust fractures, releasing energy into the magnetosphere. The twisted field lines snap and reconnect. The result is the kind of giant flare we discussed in Part 3, a release of energy so concentrated and so brief that it briefly rewrites the energy balance of the entire observable gamma-ray sky. One of the most extraordinary things that happens inside a magnetar's magnetosphere, and one of the clearest demonstrations of just how far removed its conditions are from ordinary physics, involves a process called pair production, the spontaneous creation of matter and antimatter from pure energy within the magnetic field. Under ordinary conditions, converting energy directly into matter requires a particle accelerator, a carefully controlled collision between particles at precisely calibrated energies, or the extreme conditions that existed in the first moments of the universe. Pair production, in everyday physics, is a laboratory phenomenon, rare and technically demanding. In a magnetar's magnetosphere, it happens naturally and continuously. The field is intense enough that the energy density of the magnetic field alone, without any additional input, is sufficient to spontaneously generate pairs of electrons and their antimatter counterparts, positrons, directly from the vacuum. These particles are then immediately accelerated by the field, producing additional radiation, which in turn produces additional pairs in a cascade process that fills the magnetosphere with a dense, hot plasma of particles that simply would not exist there if the field were any weaker. This process, called a pair cascade, is one of the things that makes a magnetar's immediate environment so dramatically different from even the most extreme environments found anywhere on Earth. The vacuum of space, in the ordinary sense, does not exist within a magnetar's magnetosphere. The field is too strong to allow it. Where an ordinary magnetar should have empty space, it instead has continuously self-generating plasma, built from nothing but the field itself, a situation that has no analogy in everyday physics, and that requires quantum field theory at its most extreme to describe correctly. The category of object we call a magnetar is not a single, cleanly defined type. It encompasses at least two observational subcategories that were identified and studied separately for years before the underlying connection between them became clear. The first subcategory is the soft gamma repeaters, the SGRs, which we have already discussed at some length. These are the objects that produce the repeating bursts of gamma radiation. The objects at the center of the discovery story, including the source of the 2004 giant flare, SGR 1806-20. Their defining behavior is the periodic, sometimes violent release of soft gamma rays, the relatively lower energy end of the gamma ray spectrum, and their tendency to repeat rather than producing a single event and going quiet. The second subcategory is called anomalous X-ray pulsars, abbreviated AXPs. These objects pulsate in X-rays, like ordinary pulsars, but their energy output cannot be explained by their rotation rate alone, the way an ordinary pulsar's output can. Ordinary pulsars generate their radiation primarily from the rotational energy of the spinning star, steadily extracted over time. Anomalous X-ray pulsars are producing more energy than their rotation rate could account for, and for years this excess energy had no obvious explanation. The magnetar model resolved both mysteries simultaneously. In soft gamma repeaters, the excess energy released during flares comes directly from the magnetic field. In anomalous X-ray pulsars, the persistent excess X-ray luminosity comes from the same source, a slowly decaying magnetic field, converting its stored energy into heat and radiation continuously, rather than only during dramatic flares. Both types of behavior are different manifestations of the same underlying physics. A neutron star with a field too powerful to remain stable, slowly or violently, releasing the enormous energy locked within it. This unification was one of the more intellectually satisfying moments in recent neutron star research, analogous in some ways to the realization in the 19th century that electricity and magnetism, previously thought to be separate phenomena, were actually different aspects of a single underlying force. Two observationally distinct categories of strange, poorly understood objects turned out to be the same thing viewed from different angles and from different stages of their evolution. It is easy, when discussing magnetars as a category, to lose sight of the fact that each known example is an individual object with its own history, its own behavior, its own quirks and surprises. The catalogue of confirmed magnetars, while small, contains several objects whose individual stories add important dimensions to the overall picture. In April 2013, astronomers detected X-ray emissions from a source remarkably close to Sagittarius A, the supermassive black hole at the center of the Milky Way. The source was identified as a newly active magnetar, subsequently designated SGR J145 to 2900. Located at a distance of roughly 0.3 light-years from Sagittarius A itself, making it the closest known magnetar to the galactic center, and indeed one of the closest known objects of any kind to our galaxy's central black hole. This discovery was scientifically valuable for several reasons. The galactic center is one of the most complex and difficult regions of the sky to study. Shrouded in dense clouds of gas and dust that absorb optical light entirely, making it visible only in X-rays, radio waves, and infrared light. A bright X-ray source at this location provided a rare opportunity to study the dense, turbulent environment surrounding the supermassive black hole using the magnetar's emissions as a kind of probe. In addition to studying the magnetar itself, Radio pulse timing data from SGR J1745 22900 in particular allowed researchers to measure properties of the plasma between the magnetar and Earth with unusual precision, contributing to a broader understanding of the interstellar medium in one of the galaxy's most extreme environments. Among the anomalous X-ray pulsars, a magnetar designated 1E 1048.15937 occupies a particularly interesting position in the research literature, having produced one of the clearest early demonstrations that these objects do not simply behave in a single, fixed manner, but are dynamically evolving systems. Over several years of monitoring, researchers observed this magnetar undergo significant changes in its pulsation properties, including substantial variations in the rate at which its rotation was slowing, accompanied by periods of enhanced X-ray brightness. These changes, occurring on timescales of months to years, pointed directly to the kind of slow internal magnetic evolution predicted by theoretical models of magnetar behavior, the gradual shifting and reorganization of the internal field producing observable effects at the surface. Tracking objects like 1E 1048.15937 across years and decades provides some of the most direct evidence available for how a magnetar's magnetic structure evolves over its active lifetime, turning theoretical models of field decay and crust stress into predictions that can actually be compared against real astronomical data. In March 2020, a newly discovered magnetar designated SWIFT J8818.0-1607 was detected by the Neil Gehrels Swift Observatory, a space-based telescope designed to rapidly localize and characterize gamma-ray transients. This magnetar proved to be remarkable in two ways simultaneously. First, based on its association with a surrounding cloud of material consistent with a young supernova remnant, estimates placed its age at only a few hundred years, making it potentially one of the youngest magnetars ever identified. Second, it spins with an unusually short rotation period of roughly 1.36 seconds, among the fastest rotations known for a confirmed magnetar, providing a rare glimpse at what a magnetar looks like very early in its active life, before much of its initial rotational energy has been lost. Objects like SWIFT J8818.01607 are enormously valuable to researchers attempting to understand the full life cycle of magnetars, from their violent birth in a supernova to their eventual fading into ordinary neutron star obscurity. A very young magnetar, still spinning fast and with its field relatively newly established, offers a different window into the physics than an older, slower magnetar whose field has already undergone thousands of years of decay. Together, young and old examples provide the kind of comparative dataset that allows theorists to track the evolution of these objects across their entire active lifespan, testing whether the life cycle they predict on paper matches the diversity of behavior observed in real magnetars scattered across the galaxy. There is a connection between magnetars and a question that seems entirely unrelated at first glance. Where do the heaviest elements in the universe come from? Gold, platinum, uranium, the elements that make up much of what we consider most valuable, most technologically critical, or most dangerous on Earth. For decades, astronomers understood that elements up to iron are forged inside ordinary stars, built up through successive stages of nuclear fusion as a star ages. But iron marks a boundary. Beyond iron, fusion no longer releases energy. It consumes it, Ordinary stellar fusion cannot produce the elements heavier than iron. And yet they exist, scattered throughout the universe and making up a significant portion of Earth's crust. Something else must be responsible for forging them. The leading candidate for heavy element creation, a process called the rapid neutron capture process, or the R process, requires an environment flooded with free neutrons at densities that are simply not achievable in ordinary stellar cores. Neutrons must be added to atomic nuclei faster than those nuclei can decay, building up heavier and heavier atomic structures before the system has a chance to return to stability. For a long time, the location of this process in the universe was genuinely unknown, a major unsolved problem in nuclear astrophysics. One proposed site for the R process is the merger of two neutron stars, a cataclysmic collision that produces exactly the kind of neutron-rich, extreme environment that R process nucleosynthesis requires. The detection of gravitational waves from a neutron star merger in 2017, combined with optical follow-up observations that revealed the characteristic light signatures of newly created heavy elements, provided strong evidence that neutron star mergers are indeed major contributors to heavy element production in the universe. But another proposed site, less definitively confirmed but theoretically plausible, involves magnetars specifically. In the immediate aftermath of a massive stellar collapse, if the newborn neutron star develops into a magnetar rather than an ordinary pulsar, the extreme conditions in the magnetar's early environment, including the rapid rotation, the intense magnetic field, and the violent winds of particles blown off by the early magnetar's emission, may create conditions suitable for R process nucleosynthesis in the material ejected during and shortly after the supernova. If this mechanism operates as some models suggest, then magnetars may not only be extraordinarily violent objects in their own right, but also factories for some of the rarest and most valuable elements in the cosmos, scattering newly forged gold and platinum into the surrounding interstellar medium as they spin down in the first seconds and minutes after their birth. This remains a less certain connection than the neutron star merger pathway, and ongoing research continues to assess how significant the magnetar contribution to R process element production actually is relative to other sources. But it adds yet another dimensions to the story of magnetars, connecting these extreme stellar remnants not just to the physics of violent magnetic fields and crustal fractures, but to the very chemical history of the universe itself, and by extension to the origin of the atoms making up the devices we use every day, the jewelry we wear, and the planet beneath our feet. The story of magnetars and of neutron stars more broadly entered a new chapter on September 14, 2015, though few people outside a small community of physicists noticed it at the time. On that day, for the first time in human history, a gravitational wave, a ripple in the fabric of space-time itself, was detected by an instrument on Earth. The source was two black holes merging far across the universe, but the technology that made that detection possible, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, opened a window on the universe that is now transforming our understanding of neutron stars along with everything else. 2 years later, in August 2017, LIGO and its European counterpart, Virgo, detected gravitational waves from a different kind of event. Not two black holes, but two neutron stars spiraling together and colliding. This event, designated GW170817, was observed not only in gravitational waves but simultaneously across the electromagnetic spectrum in gamma rays, X-rays, optical light, and radio waves by dozens of telescopes around the world. It was one of the most comprehensively observed events in the history of astronomy. The gravitational wave signal from GW170817 contained detailed information about the neutron stars involved, including their masses and, to some degree, their sizes. Encoded in the precise way, the signal evolved as the two stars spiraled closer together. Analyzing this information allowed researchers to place new constraints on the neutron star equation of state, narrowing down the range of theoretical models describing what neutron star interiors are actually made of. This is directly relevant to magnetars, because those same interior models determine how a magnetar's crust behaves under stress, how deep its superconducting regions extend, and whether conditions at its center might be exotic enough to involve quark matter. Gravitational waves from neutron star events also offer a potential future window onto magnetar-specific physics. A giant flare from a magnetar, if energetic enough and originating from close enough, would in principle generate a gravitational wave signal reflecting the oscillation modes of the star's structure excited by the flare. Detecting such a signal would provide information about the interior of a magnetar that cannot be obtained any other way, essentially allowing researchers to probe the star's deep structure through the ripples it sends through space-time itself. This kind of detection has not yet been achieved, but it represents one of the more tantalizing near-future possibilities in magnetar research, dependent on continued improvements in gravitational wave detector sensitivity over the coming years. Every decade of magnetar research has brought surprises, and there is little reason to expect the next decade to be any different. The field is being transformed simultaneously by new observational capabilities, new theoretical tools, and entirely new categories of data that did not exist as recently as a few years ago. Several new and upcoming observatories are expected to significantly advance our ability to study magnetars. In X-ray astronomy, instruments with improved spectral resolution and time resolution will allow researchers to track individual magnetar flares with a level of detail previously impossible, potentially revealing the fine structure of how a starquake unfolds in real time, rather than just its overall energy output. Radio observatories like the Square Kilometre Array, currently under construction across sites in South Africa and Australia, will eventually provide sensitivity and resolution far beyond current capabilities, potentially identifying and monitoring magnetars previously too faint to detect and catching fast radio burst events with the precision needed to definitively connect them to specific physical mechanisms within individual magnetars. Space-based gravitational wave detectors, planned for launch in the coming decades, will extend the frequency range of gravitational wave astronomy into regimes where neutron star oscillation modes, including those excited by magnetar starquakes, become detectable. This prospect represents one of the most genuinely exciting frontiers in the field, the possibility of directly measuring the interior structure of a magnetar, not through its light or its magnetic field, but through the space-time disturbances generated by its own vibrations. One of the less glamorous, but practically significant developments in modern magnetar research involves the application of machine learning. to the enormous volumes of data generated by continuous sky monitoring programs, identifying a genuine magnetar burst within the data stream from a gamma ray or X-ray telescope, distinguishing it from cosmic ray events, instrument noise, and the background of other astrophysical sources requires pattern recognition across datasets too large for manual inspection alone. Machine learning systems trained to recognize the characteristic spectral and timing signatures of magnetar bursts have already demonstrated the ability to identify events in archival data that were previously missed, effectively mining older observations for signals that human analysts did not catch at the time. As these systems improve, and as the volume of continuous sky monitoring data grows with each new generation of instruments, they may enable a substantially more complete census of magnetar burst activity across the galaxy than is currently available, providing the statistical foundation needed to answer some of the field's most persistent questions about how frequently giant flares occur, how the burst rate evolves over a magnetar's lifetime, and how the behavior of known magnetars compares to the predicted behavior of the broader, still largely undetected population. It is worth, before concluding this section, being genuinely honest about the scale of what remains us unknown in magnetar science, not to undermine the remarkable progress made over the past 30 years, but to place that progress in accurate context. We do not yet have a fully predictive model of magnetar formation. We cannot look at a massive star and say with confidence whether it will produce a magnetar when it collapses. We do not fully understand the detailed mechanism connecting internal magnetic field evolution to crustal fracture and giant flare emission. The broad outline is established, but the precise physics, in complete mathematical detail, remains a subject of active research. We do not know with certainty what the interior of a neutron star, magnetar or otherwise, is made of at its very center, whether quark matter exists there, and in what form remains genuinely unresolved. We do not know whether fast radio bursts are primarily produced by magnetars, or whether magnetars account for only a fraction of the observed population, with other mechanisms responsible for the remainder. We do not know how many magnetars exist in total throughout our galaxy, because the currently confirmed catalog almost certainly represents only a fraction of the actual population, skewed toward objects that happen to be active, close enough, and oriented favorably relative of Earth. Each of these open questions is not a failure of the field. It is a statement of where the frontier currently lies, and a map of the work still to be done by researchers who will spend the next decades steadily narrowing the gaps. At the very end of a long journey through the physics, the history, and the implications of magnetars, it is worth stepping back one final time and asking the simplest possible version of the question we have been exploring. What does it mean that objects like this exist? One way to understand the significance of magnetars is to place them within the broader context of what we know about the universe's capacity for extremes. The cosmos contains objects spanning an enormous range of scales and conditions. Gentle, rocky planets where liquid water sits quietly on a surface. Roiling, nuclear furnace stars burning for billions of years. Cold clouds of gas drifting for millions of years in the intergalactic dark. Supermassive black holes consuming material at the centers of galaxies, outshining everything else in those galaxies combined. The universe is not uniform. It does not settle into a single moderate condition. It fills every available niche. Every regime permitted by the laws of physics, with something. Magnetars occupy one end of a particular spectrum. The extreme of magnetic field strength accessible to matter in the current universe. They are, in a meaningful sense, the magnetic universe's most extreme statement, the answer to the question of how strong a magnetic field can become under natural conditions. The answer turns out to be far stronger than most physicists would have guessed a century ago. Strong enough to deform atoms, strong enough to fracture the strongest material permitted by nuclear physics, strong enough to briefly alter the ionosphere of a planet on the far side of a galaxy. Understanding that this is possible, that the laws of physics we study in laboratories and describe in textbooks permit a natural object to generate a field this powerful, changes something subtle but important about how we understand those laws. The physics we know is not a collection of modest, well-behaved phenomena. It is a set of rules that, under the right conditions, permits monsters. And yet, for all the genuinely staggering physics involved, magnetars are also, in their own way, a deeply human story. They were discovered because human beings built satellites originally intended to monitor nuclear weapons tests. And those satellites happened to record something far stranger than any weapon. They were explained because two researchers, Robert Duncan and Christopher Thompson, were willing to propose something that initially seemed implausible to many of their peers. And were right. They were confirmed by a combination of theoretical work, careful observation, and a willingness to take unusual signals seriously rather than dismissing them as instrument errors. The knowledge we have of magnetars, everything in this documentary, every number, every physical description, every unsolved mystery exists because individual human beings chose to spend their careers looking carefully at the sky, building instruments sensitive enough to detect events happening 50,000 light years away, and then thinking carefully about what those events meant. It is an almost unreasonably small number of people, working across several decades, who have built the collective understanding we now have of one of the most extreme categories of object in the known universe. This is one of the things that makes the story of magnetars not just a story about exotic physics, but a story about human curiosity in its most sustained and productive form. We did not need to understand magnetars to survive. No human civilization has ever been threatened by one, and none will be in any foreseeable future. But we wanted to understand them, and the wanting extended across decades and expressed through careful observation, patient theory building, and willingness to revise what we thought we knew, has produced something remarkable, a genuine, if incomplete, understanding of one of the most extreme environments the universe is capable of creating. We have now covered the formation of magnetars, the extraordinary physics of their magnetic fields, the interior structure from their thin plasma atmosphere, down to their speculative quark matter cores, the giant flares that briefly rewrite the energy balance of the observable sky, the discovery story spanning from Cold War satellites to the theoretical breakthrough of the early 1990s, the connection to fast radio bursts, the implications for heavy element production in the universe, and the future of the field. What we have not been able to cover, because it has not yet been discovered, is whatever comes next. Every major chapter in the magnetar story has contained a surprise. Soft gamma repeaters were surprising. The field strengths required to explain them were surprising. The 2004 giant flares was surprising even to researchers who had spent years studying the objects capable of producing it. The connection to fast radio bursts was surprising. The discovery of a magnetar close to the galactic center supermassive black hole was surprising. There is no reason to believe the surprises have ended. Magnetars have a history of exceeding expectations, of being stranger, more energetic, more connected to other areas of astronomy, and more revealing of fundamental physics than anyone predicted at any given moment in the research timeline. The next major discovery in magnetar science is already out there, encoded in photons currently traveling toward Earth, in gravitational waves not yet strong enough to detect with current instruments, in archival data not yet analyzed with the right software, or in a theory not yet conceived by a researcher who has not yet been born. That is the final mystery magnetars offer us, and it is the best kind. Not a gap in knowledge that makes us feel ignorant, but an open door in knowledge that makes the universe feel larger than it did before we started looking. Somewhere in the galaxy right now, a magnetar's crust is accumulating stress. Magnetic field lines are twisting tighter. The crystal lattice of the strongest material in the universe is being pushed fractionally toward its breaking point, and eventually, in a fraction of a second, it will break, and the universe will send us another signal. And we will be here, with our instruments and our curiosity and our still incomplete but growing understanding, to receive it. We have used the word starquake several times in this documentary, and each time we have treated it as a vivid but ultimately approximate comparison to the earthquakes that periodically shake our own planet. It is worth, at this stage, doing justice to the actual physics involved. Because a starquake is not simply a large earthquake, the way a hurricane is simply a large thunderstorm. A starquake is a categorically different kind of event, one that involves physics operating simultaneously on the scale of atomic nuclei and on the scale of an entire stellar remnant, and understanding it more fully illuminates why magnetars release such extraordinary amounts of energy in such extraordinary short intervals. Imagine for a moment the outer crust of a magnetar as a thin, extraordinarily rigid shell, a few 100 meters thick, wrapped around an inner core of super-dense material. This shell is the neutron star crust we described earlier, composed of atomic nuclei locked into a crystal lattice of almost unimaginable strength. Now thread magnetic field lines through this shell, lines that do not lie flat and orderly but twist and curve as the field evolves over time, exerting force on the crystal lattice in multiple directions simultaneously. Over years and decades, the magnetic field's slow evolution gradually changes the distribution of stress within the crust. Some regions are under tension, others under compression. The crystal lattice deforms fractionally, accumulating strain at certain points, the way a stick of hard wood accumulates internal stress as it is slowly bent. As long as the stress remains below the material's yield strength, the enormous strength of the neutron star crystal holds, nothing visible happens. But the yield strength of even the strongest material in the universe is not infinite. There is a threshold beyond which the crystalline structure cannot absorb more deformation elastically, the way a bent ruler snaps back when released. Beyond that threshold, the structure fails. Not gradually, not in stages, but suddenly, as the accumulated energy releases at essentially once, propagating a fracture through the crystal at close to the speed of sound within the crust, which, in this material, is itself an extraordinary fraction of the speed of light. This is one of the details that makes starquakes so energetically extreme. On Earth, earthquake ruptures typically propagate along fault lines at a few kilometers per second, a fast but not extraordinary speed by physical standards. In the crust of a neutron star, the speed of sound through the material is a significant fraction of the speed of light, potentially tens of thousands of kilometers per second, depending on the specific properties of the material. At the depth of the fracture, the rupture of a starquake, propagating at such speeds through such dense, energetically loaded material, releases its stored energy not over seconds or minutes, the way a large terrestrial earthquake might, but over milliseconds or less, an event so brief that most electronic timing systems would record it as essentially instantaneous. This extreme compression of the release timescale is a central reason why the power output of a giant flare is so staggering. It is not simply that a large amount of energy is released. It is that an enormous amount of energy is released in an interval so brief that the effective power energy per unit time reaches levels that dwarf almost every other known astrophysical event. When the crust fractures, the energy does not simply radiate away directly into space as gamma rays. The process involves several intermediate steps, each one transforming the mechanical energy of the fracture into progressively more energetic radiation through the magnetosphere. The fracture launches alpha waves, a type of wave unique to magnetized plasma, propagating outward through the magnetosphere, along the twisted field lines. As these waves travel outward, they accelerate charged particles within the magnetosphere to enormous energies. These accelerated particles emit radiation through a process called synchrotron emission, spiraling around the field lines and converting their kinetic energy into photons across a wide range of energies, including the gamma rays and X-rays we ultimately detect. The specific mix of photon energies produced and how it evolves over the first seconds and minutes of a giant flare provides researchers with detailed diagnostic information about conditions within the magnetosphere at the moment of the event. The initial spike of the giant flare, lasting only a fraction of a second, is followed by a more slowly decaying tail of emission that can persist for several minutes, pulsating at the rotation period of the magnetar. This pulsating tail results from a fireball of hot plasma trapped within the magnetosphere, immediately after the initial fracture, rotating with the star and gradually cooling and dimming as it radiates away its energy. Analyzing the detailed timing and spectral evolution of both the initial spike and the subsequent decaying tail allows researchers to reconstruct, at least partially, the geometry and dynamics of the magnetosphere during and after the event, turning each observed giant flare into a detailed physical diagnostic rather than simply a record of energy released. One of the most useful ways to understand just how extreme magnetars are is to place them honestly within the broader context of known astrophysical energy scales, comparing their output during a giant flare to the other most energetic events known to occur in the universe. Our Sun, for all its apparent power, sits far down the energy hierarchy by cosmic standards. The Sun's total power output, sustained continuously across its entire surface, amounts to roughly 3.8 times 10 to the 26th watts, a number so large it is essentially meaningless without comparison the most powerful solar flares, classified as X-class events, and occasionally powerful enough to disrupt radio communications and satellite operations on Earth, represent a momentary increase above the Sun's background output, releasing energies measured in the range of 10 to the 25th joules over the course of several minutes. A magnetar's giant flare, as we have established, can release energy comparable to what our Sun produces across 100,000 years. In terms of momentary power output during the brief initial spike of the flare, lasting perhaps 1/10 of a second, the effective power output reaches values trillions of times greater than the Sun's steady luminosity. A solar flare, by comparison, is an irrelevant fluctuation, the supernova that creates a neutron star, the explosion of a massive star at the end of its life, is itself one of the most energetic events in the observable universe. A typical core collapse supernova releases a total energy, summed across all forms, including the flood of neutrinos produced in the collapse, of roughly 10 to the 44 joules, an amount of energy that briefly outshines the combined steady light output of every star in an entire galaxy. A magnetar's giant flare releases, in that same brief fraction of a second, a total energy measured in the range of 10 to the 42 to 10 to the 46 joules, depending on the event, comfortably within the same order of magnitude as a supernova's total electromagnetic output, and in some of the most extreme cases potentially rivaling it. The critical difference is time. A supernova's light output unfolds over weeks to months as the expanding debris cloud gradually dims. A giant flare's energy release is concentrated into milliseconds to seconds. This concentration of energy into such a brief window is what makes the instantaneous power output of a giant flare so extraordinary relative to almost anything else in the known universe. The most energetic individual events known to occur in the universe, other than the Big Bang itself, are gamma-ray bursts, brief flashes of gamma radiation originating from extremely distant galaxies, the most powerful of which are believed to result from the collapse of unusually massive stars, or from the merger of two compact objects. The most energetic gamma-ray bursts can release total energies measured in the range of 10 to the 47 joules or greater, genuinely overwhelming the energy output of a magnetar's giant flare by a factor of 1,000 to 1,000,000. This places gamma-ray bursts beyond magnetars in the energy hierarchy, though the comparison requires some nuance. The most energetic gamma-ray bursts are events happening in galaxies billions of light-years away, representing the deaths of particularly extreme objects, rather than the starquakes of a surviving stellar remnant. A magnetar giant flare, by contrast, is generated by an object that survives the event, continues existing, and will eventually produce another one. A magnetar is not a one-time explosion, but a repeating source of extreme energy releases, separated by months to years between events, which means its total lifetime energy output may accumulate to values that deserve comparison with even the most extreme single events in the universe. The 2004 flare from SGR 180620, as we have established, was energetic enough to measurably affect Earth's ionosphere from 50,000 light-years away. For comparison, the nearest confirmed gamma-ray burst known to have significantly affected Earth's atmosphere occurred roughly 440 million years ago, originating from within our own galaxy, and is speculated by some researchers to have contributed to one of Earth's major mass extinction events, A magnetar's giant flare is not a gamma-ray burst, but it is the closest naturally occurring analog to one that happens routinely, repeatably, and in some cases within our own galaxy. There is a dimension to the study of magnetars that rarely appears in scientific papers, but that is very much present in the actual practice of the field. The human experience of pursuing knowledge about out objects so extreme that they challenge our intuitions at every step. Researchers who work on magnetars spend careers grappling with a particular cognitive dissonance. Their mathematical tools, the equations they use to describe magnetar behavior, are extensions of physics developed and tested under conditions that are, by cosmic standards, extraordinarily gentle. Quantum electrodynamics was built up from experiments conducted in laboratories, using apparatus made of metal and glass, studying electrons and photons under conditions a trillion times less extreme than what exists at a magnetar's surface. Applying these equations to magnetar conditions requires a kind of professional confidence in the deep reliability of physical law, a trust that the same equations that describe an electron's behavior in a university physics lab will continue to describe it correctly when the magnetic field is scaled up by a factor that boggles the imagination. Sometimes that confidence has been rewarded. Predictions made using standard quantum electrodynamics applied to magnetar field strengths have been confirmed by observation. Vacuum birefringence, the bending of light's polarization by extreme magnetic fields, is not some exotic new physics invented specifically for magnetars. It is a prediction of the same theoretical framework that describes how light interacts with matter in a laboratory. The confirmation of that prediction in magnetar observations is a confirmation of the deep reliability of physics across scales we can barely imagine. And sometimes the observations reveal genuine puzzles, behaviors that do not fit cleanly into existing models, events that require refinement or extension of current theories. The anti-glitch phenomenon, the unexpected slowdown of a magnetar's rotation, rather than the expected speed-up, spent years without a fully satisfying theoretical explanation after its initial observation. The specific details of how some magnetar giant flares evolve over their first seconds continue to challenge simple models. These are not failures of physics. They are the texture of real science, the constant interplay between theory and observation that gradually sharpens understanding, without ever fully exhausting the universe's capacity for surprise. The researchers who have built the field of magnetar science have spent their careers, in many cases, studying a handful of objects, each one behaving slightly differently, each new observation refining, but rarely simply confirming the picture built by the previous one. It is slow, patient, demanding work, conducted mostly without public attention. At the intersection of nuclear physics, astrophysics, electromagnetic theory, and computational modeling. The result of that work is what you have been listening to throughout this documentary. A genuine, hard-won, still incomplete but continually growing understanding of some of the most extreme phenomena the universe is capable of producing. That is not nothing. That is, in fact, one of the more remarkable things our species has ever managed to do. We have now traveled from the ordinary death of a massive star to the extraordinary birth of a magnetar. We have examined the field that defines it, the crust that it breaks, the flares that briefly rewrite the observable sky. We have looked inside it, as far as current physics allows, finding neutron superfluids and speculative quark matter in a superconducting core. We have traced the discovery story from Cold War satellites to Canadian radio telescopes. We have connected magnetars to fast radio bursts, to heavy element production, to the future of gravitational wave astronomy, and to the deepest unanswered questions in nuclear physics. And yet, what strikes most researchers in this field at the end of all of this is not what we know. It is the shape of what we do not know, the way the edges of our understanding outline something genuinely vast, still waiting to be explored. We do not know exactly what happens inside a magnetar in the final moments before a giant flare. We have models, we have predictions, we have post hoc analyses of events already recorded, but the detailed real-time physics of a starquake as it unfolds, the precise sequence of events connecting the first microscopic fracture in the crystal lattice to the satellite-saturating burst of gamma rays, arriving at Earth, fractions of a second later, remains beyond our current ability to fully reconstruct. Future observatories, with better time resolution and broader wavelength coverage, may change this. We do not know how many more magnetars wait to be discovered. The 30-odd confirmed objects in the current catalogue represent only the tip of an iceberg, whose full extent we cannot yet see. The majority of magnetars are likely too old, too faint, or oriented too unfavorably relative to Earth to appear in current surveys. Better instruments will find them. We do not know whether there are places in the universe where magnetar-like objects exist under even more extreme conditions than the examples we have found. Some theoretical models suggest that the magnetars we currently know, extreme as they are, may not represent the absolute upper limit of what magnetic field strengths nature can produce. If objects exist with fields even stronger than the most extreme known magnetars, they may behave in ways that current models do not fully anticipate. And we do not know, perhaps most intriguingly of all, what the universe looked like in its earliest moments, when magnetic fields of potentially extraordinary strength may have permeated the cosmos before stars even existed. The connection between magnetar physics and the possible role of primordial magnetic fields in the early universe is a speculative but scientifically serious area of inquiry, one that places these small, violent stellar remnants within a much larger cosmological context that extends all the way back to the first fractions of a second after the Big Bang itself. These open questions are not embarrassments. They are invitations. Each one represents a direction in which our understanding can still grow. A promise that the study of magnetars has not exhausted what it has to teach us about the universe. Somewhere in the darkness beyond the reach of current instruments, magnetars we have not yet discovered continue their slow magnetic violence, fracturing, flaring, fading, sending signals toward us at the speed of light that will arrive in years or centuries or millennia, depending on their distance, patient beyond any human concept of patience, violent beyond any human concept of violence, and indifferent to both, as all the universe's extreme physics is indifferent, following the same laws that govern everything from a compass needle to the first second of cosmic time, with perfect, beautiful, terrifying consistency. That is what a magnetar is. That is why it is worth understanding. There is a quality of magnetar science that tends to get lost when the discussion focuses, as it naturally does, on the dramatic events, the giant flares, the starquakes, the satellite-saturating bursts of gamma radiation. That quality is the long, quiet intervals between events, stretching across years, sometimes decades, during which a magnetar simply exists in the darkness, spinning, cooling fractionally, accumulating stress within its crust, showing no obvious sign to any observer that it is anything other than an ordinary, unremarkable neutron star. These intervals matter for several reasons. They are, first and most practically, the periods during which monitoring programs must maintain vigilance without obvious reward. Tracking the slow evolution of a magnetar's spin rate, its surface temperature, and its persistent X-ray emission for months and years at a time, in the hope of detecting the subtle precursor signals that might eventually reveal something about the physics of the next event, before it arrives. Whether magnetar giant flares can be predicted in advance. The way some volcanic eruptions or earthquakes can be anticipated through monitoring of precursor signals is one of the more practically interesting open questions in the field. There is suggestive evidence from some magnetars that the rate of smaller bursts, the minor crackling of the crust that falls far below the threshold of a giant flare, increases in the period leading up to a more energetic event. Something that might in principle serve as a warning sign if the relationship were well characterized and reliable. But the evidence is not yet strong enough to support confident prediction. And given the rarity of giant flares, accumulating the statistical base needed to establish a reliable precursor signature may take many more decades of continuous monitoring. The quiet intervals also carry a subtler scientific significance. During these periods, the magnetar is not simply waiting to do something dramatic again. It is evolving. The internal magnetic field is shifting, fractionally, continuously. The crust is responding to those shifts, accumulating new stress at some points, perhaps partially relieving it at others. The star's rotation is slowly decelerating, its surface temperature very gradually declining. Each of these slow processes, playing out across years, is encoding information about the magnetar's interior physics that patient observers can in principle read if they have the instruments sensitive enough and the patience to use them across the necessary timescales. This is the quiet face of extreme physics. Not always the sudden violent release, but the slow, patient accumulation of force that makes the violent release inevitable. The starquake lasts a millisecond. The stress that produces it builds over years. Understanding both timescales and the connection between them is essential to understanding what magnetars actually are. Throughout this documentary, we have mentioned distances casually, saying that a given magnetar sits 50,000 light-years away, or that another is located 20,000 light-years from Earth. These numbers appear frequently in discussions of astronomy, and they can, with repetition, begin to sound like ordinary large numbers, rather than what they actually are. Distances so vast that they place these objects in a category of remoteness that the human brain cannot genuinely process intuitively. A light year is the distance light travels in a full year, moving at approximately 300,000 kilometers per second, the fastest speed permitted by the laws of physics. In 1 second, light crosses a distance of roughly 7 times the circumference of Earth. In 1 minute, it travels from Earth to the Moon and back many times over. In 8 minutes, it crosses the distance from Earth to the Sun. In 4 years, it reaches the nearest star beyond our own solar system. In 50,000 years, moving continuously at this speed without pause, It crosses the distance to SGR 1806 to 20, the source of the 2004 giant flare. The light from that flare that reached Earth in December 2004 began its journey 50,000 years earlier, at a moment deep in the prehistoric past out of our species, before the development of agriculture, before the construction of any monument, before any written language. It traveled for 50,000 years across the darkness of the Milky Way and arrived at Earth in the middle of a perfectly ordinary day in 2004, where it triggered alerts on multiple satellites and briefly altered our planet's upper atmosphere. This is the scale at which magnetar science operates. Every piece of data we have ever collected about these objects traveled for distances measured in tens of thousands of years to reach our instruments, meaning that what we observe is always a snapshot of the distant past rather than the present state of the object. When we watch a magnetar's brightness slowly change over months, we are watching a process that unfolded tens of thousands of years ago. The magnetar we are observing may, right now in its own present, have already faded into an ordinary neutron star. Its active phase ended centuries ago. Or it may have produced another giant flare last year, whose light will not reach us for another 49,999 years. We study the past and call it the present, because at these distances, there is no alternative. This is not a weakness of astronomy. It is simply the nature of a universe too large for any signal, even light itself, to cross in human timescales. But it means that the picture we have of any individual magnetar is always incomplete in a specific and unavoidable way, separated from the current state of the object by a gulf of time that no improvement in instrumentation can bridge. There is something profound in this realization. The universe keeps its own counsel on timescales that dwarf anything human civilization has ever attempted to measure, plan for, or imagine. Magnetars are extreme in their physics, but they are also extreme in their temporal and spatial remoteness, embedded in a cosmos where the word now becomes genuinely ambiguous when applied to objects across galactic distances. And yet we study them anyway. We build instruments, maintain monitoring programs, refine theoretical models, and gradually accumulate understanding, knowing that the picture will always be incomplete, knowing that the objects we study may have changed irrevocably in the eons it took their light to reach us. We do this not because we expect to ever have a complete, real-time picture of these objects, but because even an incomplete, time-delayed picture reveals genuine truths about the physics that governs them. And by extension, the physics that governs everything, including the matter and energy that make up us. That continuity, from the electromagnetic behavior of atoms in a laboratory to the behavior of a magnetar's crust under magnetic stress, 50,000 light-years away, is perhaps the most fundamental reason magnetar science matters. Not because magnetars will ever threaten us, not because understanding them has immediate practical applications, but because the universe is one place, governed by one set of laws, and understanding those laws in their most extreme expressions deepens our understanding of everything those laws produce, from the gentlest chemistry of a living cell to the most violent starquake in the dark heart of the Milky Way. We began this documentary with an object that does not look impressive through a telescope. We end it appropriately in the same place. A small, faint point of light, spinning in the dark, across a gulf of space and time that dwarfs any distance human beings have ever physically crossed. it is not much to look at. It is perhaps the strangest thing in the galaxy, and we are fortunate in the deepest sense to live in an era when we can say that we have begun, at least, to understand why. Every piece of knowledge in this documentary arrived through an instrument. It is worth spending a moment with this fact, because the history of magnetar science is also, inseparably, a history of the machines human beings built to receive information from across the galaxy, and what those machines have taught us about how to look. The earliest signals that would eventually be understood as magnetar activity arrived through instruments that were never designed for the purpose. The Vela satellites of the 1970s were engineering achievements of the Cold War, precision detectors built to monitor gamma radiation in Earth's vicinity for signs of clandestine nuclear testing. Their sensitivity to gamma rays was genuine but narrow, focused on the specific signatures of nuclear weapons rather than the broad spectrum, rapidly variable emission of astrophysical transients. When SGR 052666 erupted in March 1979, these satellites recorded it because they were looking at the sky for something else entirely, and the signal happened to fall within the range they were designed to detect. This is a recurring pattern in the history of astronomy. Instruments built with one purpose inadvertently becoming windows onto phenomena their designers never imagined. The microwave receivers that led to the discovery of the cosmic microwave background radiation, the relic glow of the early universe, were originally built for satellite communications research. The radio receivers that detected the first pulsar were designed for an entirely different kind of astrophysical survey. Science is full of these accidents, these moments when the universe inserts itself into research designed to find something else entirely. The generation of instruments that followed the Vela satellites were more deliberately designed for high-energy astrophysics, though still not specifically for magnetars, which as a category did not yet exist in any theoretical sense when many of these instruments were being built. The Compton Gamma Ray Observatory, launched in 1991 and operating for nearly a decade, catalogued gamma ray sources across the sky with far greater sensitivity and resolution than had been previously possible, contributing substantially to the growing dataset of soft gamma repeater observations that theorists were attempting to explain during precisely the years when Duncan and Thompson were developing the magnetar model. Later instruments, including the Rossi X-ray Timing Explorer, the Swift Observatory, and the Fermi Gamma Ray Space Telescope, brought progressively more sophisticated timing and spectral capabilities to bear on magnetar observations, enabling the kind of detailed characterization that transformed magnetars from an inferred category into a richly documented class of objects with individual, well-characterized histories. Each of these instruments represented the culmination of years of design work, testing, launch preparation, and in-orbit calibration before it could contribute a single data point to magnetar science. The patience required to build and operate these machines, sustained across timescales measured in decades, mirrors in its own way the patience the universe exercises in its own processes, accumulating magnetic stress for years before releasing it in a fraction of a second. What makes the current moment in magnetar research particularly interesting is not any single instrument but the convergence of multiple observing platforms operating simultaneously across different wavelengths and different physical messengers: radio waves, X-rays, gamma rays, and increasingly gravitational waves, each sensitive to different aspects of the same underlying physics. This multi-messenger approach, as it is called in contemporary astrophysics, allows researchers to assemble a more complete picture of any individual event than any single instrument could provide alone, triangulating on the physics from multiple independent directions simultaneously. The 2020 detection of a fast radio burst from the Magnetar SGR 1935+2154 was itself a multi-messenger event, simultaneously observed in radio waves, by chime, and in X-rays, by instruments aboard the Nixer Observatory, aboard the International Space Station, and the InSight HXMT satellite, operated by China. The convergence of these independent observations, each capturing a different aspect of the same event, provided the clearest possible confirmation that the radio burst and the X-ray burst originated from the same source and produced a combined dataset far more diagnostic of the underlying physics than either radio or X-ray data alone could have been. This is how the field continues to advance. Not through any single dramatic breakthrough, but through the patient accumulation of multi-wavelength observations matched against progressively refined theoretical models, refined again by each new observation, a slow spiral toward deeper understanding that has no obvious terminus. Magnetars will be studied, observed, and argued about by astrophysicists for as long as the field of astrophysics exists, because they represent a category of phenomena at the intersection of nearly every frontier question in fundamental physics, from the equation of state of dense matter to the limits of quantum electrodynamics, to the origin of the universe's heavy elements, to the nature of the most energetic transient events in the observable cosmos. That combination of connections to so many different open questions in so many different areas of physics is ultimately what makes magnetars not just a fascinating, specific topic, but a genuinely important one for the broader project of understanding the physical universe. They are not an isolated curiosity. They are a node in a web of unsolved problems, and each step toward understanding them is a step toward understanding something larger. The story of magnetars is the story of the universe pushing its own physics to an extreme, and of human beings equipped with patience and instruments, and the willingness to revise what they thought they knew, pushing back with careful observation and honest inquiry. It is, in the end, a story about what curiosity can accomplish when it is sustained, well-equipped, and aimed at something genuinely worth understanding. And it is far from finished. Everything described in this documentary reflects the current state of magnetar science as understood through peer-reviewed research and established astrophysical consensus, where scientific questions remain genuinely unresolved. This documentary has attempted to represent them honestly, distinguishing between established findings, well-supported theoretical models, and areas of active debate or speculation. The field of magnetar research is young by the standards of most physical sciences. The theoretical framework explaining what magnetars are was only fully established in the 1990s. The connection between magnetars and fast radio bursts is less than a decade old. New observational data, arriving continuously from space-based and ground-based observatories, continues to refine the picture presented here. Some details described as well-supported theory may, in coming years, be revised in light of new evidence. This is not a limitation of the science. It is what science in an active frontier area looks like. The numbers cited throughout, energy outputs, magnetic field strengths, distances, timescales, and material properties, are drawn from the published scientific literature and represent current best estimates rather than precisely fixed values. Different research groups, working from different observational datasets and different theoretical assumptions, sometimes arrive at somewhat different numbers for the same physical quantities. Where a range of values exists in the literature, this documentary has generally presented a representative central estimate, while acknowledging where significant uncertainty remains. The goal throughout has been accuracy tempered by appropriate humility about what is known, what is inferred, and what remains genuinely unknown, in service of the most important objective any science documentary can have: conveying an honest picture of one of the universe's most extraordinary phenomena to curious, intelligent people who deserve to understand it as clearly as current knowledge allows. There is one final thought worth leaving with anyone who has spent time with this subject. Magnetars are, in many respects, the universe's most effective demonstration that the laws of physics, the same laws we test in laboratories, derive mathematically in textbooks and apply to everything from the orbit of satellites to the operation of medical scanners, have no upper limit built into them. There is no clause in quantum electrodynamics that says fields only become this strong in theory, never in practice. There is no note in nuclear physics saying that matter only reaches this density in our equations. The equations permit what they permit, and the universe, indifferent to human intuition about what should be possible, builds accordingly. Magnetars exist because the physics allows them to. They are extreme because the physics permits extremes, and they are discoverable because the same physics that creates them also creates light. And light, patient and incorruptible, carries their story across 50,000 light years to instruments built by curious creatures on a small planet who wanted, simply and profoundly, to understand what the universe contains. That is enough. That has always been enough. That will continue to be enough for as long as the universe keeps its secrets, and we keep asking what they are.